Welcome everybody. This is Pancake and I'm pleased to present you the keynote for r2con 2020. Your favorite open source reverse engineering conference. This time it's purely an online event. So I guess that you heard that I was covering the text. I guess that you heard something about the virus, and don't worry if you missed the flight to Barcelona. This time we are doing everything online, so you can basically attend the conference from home. You don't need to take any flight, book any hotel, whatever. So we won't put you at risk. We'll organize everything from the very beginning, thinking on the COVID. So as long as we didn't want to have anything physical, we managed to reduce the price and also the organization cost a lot. And so yeah, there is some stuff that we will probably miss from an online event. So let's see. In virtual events, we don't have the hassle of real life, which probably sounds great, but where is the beer? Well, I guess that during the lockdown, everybody learned some stuff about cooking, brewing stuff, or finding new beers. So I guess that it's time for you to share the pictures and all your new skills into that in this channel. This way, we try to get the warmth of the community into the network. We decided to pick the r2con 2020 hashtag in Twitter, so you can publish your stuff in there. So any question, any pictures, screenshots, whatever, feel free to post them. Even if it's not a physical event, we would like to have some stuff online. So as I said, virtual events don't really need to have a lot of costs. For example, traveling, renting the place, recording materials, buying all the food, drinks, and all the immense hours of work, moving boxes up and down, like everybody who have been helping in previous years have been suffering. But even if it was like a hassle, I really miss that. So as long as in r2con it's a non-profit organization and we are making this conference only for the community, we decided to reduce the price to €0. So that's quite cheap. Even at this price, we decided to submit the merchandising pack to all the speakers. And we will submit also the same merchandising pack to all the participants of the CTF, r2words, and Google Summer of Code at the end of the event. But right now we are replacing the website, we are updating it, and you have a new link. Well, it's basically a form that you can fill at the bottom of the website if you want to get some more merchandising for yourself. The merchandising pack comes with a t-shirt, the flag, some stickers, and the mask. So this is a question that many people have been asking, is that, well, we are recording everything. We will have like everything recorded online. We are also recording offline. And at the end of the event, we will talk with all the speakers and we'll publish all the recordings. So don't worry if you are missing some of the talks or the... so you will be able to follow them offline. If you want to talk or make any question about the YouTube, use the YouTube channel. And also there is like a Telegram chat that you can also use for making questions there. At the end of each presentation, we will show you a Q&A time, which is slides from Google Slides that you can basically submit your questions in a URL, and the speaker will be able to answer you. Obviously, as we are making everything in Telegram, like the attendees channel, the speakers channel, all the conversation stuff, it's happening there. You may be able to find all the speakers from this conference in Telegram, so feel free to hang out in the chat and talk with them directly if you have any question. We have like 19 talks this time. As long as we are not depending on physical place or some schedules or some physical problems, we can hold much more talks. So This time it's 19, and we are covering different topics from symbol execution, hardware reverse engineering, Slate and Ghidra integration, signature matching, deobfuscation, iOS and Android reverse engineering, also malware hunting, and there is also some stuff related to freedom. For the Google Summer of Code, there will be a presentation from all the students that have been working during the summer. That they will be presenting the new updates of their work. So basically all the stuff that they have been working during the summer, and this is improving the debugger support, as well as the integration with Ghidra, and improving the type analysis, as well as the writing an updated decompiler widget for Qt. For the workshops, we decided that, well, it's hard to follow a training, basically because there is a lot of interruptions, a lot of questions, people want to make some tests, and everything is working at the first try. So we decided to change the training word for workshops, which aim to be more dynamic. They should be easy to follow, and mentors are also available online, so you can talk with them, you can ask stuff directly in the chat. So they can answer you at the moment, or maybe later if they have some time after the conference. As I said before, all the talks and workshops will be recorded and published. Okay, the two workshops are R2 which is the same that we held last year, and there is also an SMT training that it's done by the same people that was done last year. I hope you enjoy them, and feel free to make any question or whatever you need in the chat. Let's go for the competitions. This time we have only two competitions. We are having the Capture the Flag organized by Murphy. This will be the registration for the CTF will be open today at 7 p.m. Right now it's 5 p.m., so we are taking everything in Barcelona time. It will start on Thursday, so it's tomorrow, so you can register today and start playing tomorrow, and it will finish on Saturday. The idea is that at the end of the conference, we will announce who are the winners, and you will get the prize, as I said before. So there are like easy, medium, and hard challenges from different architectures that you should be reverse engineering using R2. And if you manage to solve them, you should probably write some lines about how you did that using R2. So I would like to thank to Mario Vilas, Tony Torralba, Eloy Sanfelix, Gotham, Grant Douglas, Roberto Gutierrez, Eduardo Novella, and Alex Sule. They are all the people that have been working behind the scenes on the CTF, and I'm really happy that all their crackmates and all the tests that they have been writing, and they will be available in the CTF. So I hope that you have some fun following this game. The other competition that we are holding is the R2 Wars. R2 Wars have been like a traditional competition in this conference. It has been a lot of fun. At the beginning, people was not really understanding the purpose of the game, and it's kind of like core bots competition, which basically there are like two programs running in the same memory space, trying to make the other program crash. The thing is that this game was written in one night, just for fun, using Python and R2 pipe. So it's using R2 behind the scenes, and it's using a seal for emulating the code. So Squatter decided to write the code in C#. So there is like a web UI that you can use for launching and testing your bots. But there is a presentation right after me that will give you more details and some tricks in order to participate in this game. Basically, the main purpose of this game was to be able to find excuses to test the assemblers, the disassemblers, as well as the emulation, and trying to find the right balance of execution cost of each instruction. Because the thing is that each turn is executing not the whole instruction, but it's taking some extra time depending on the cost of the instruction. So it's accessing memory is slower than accessing resistors, for example, and stuff like that. So we'll see more about R2 Wars later. And at the end of the conference, there is like a chiptune party. We are having 5 different artists that will be playing on Saturday night. I don't know if you really like chiptune, but I love it, and I know there is a bunch of people attending the conference that also love this lo-fi music. So yeah, I hope you have fun. So thanks to 40boy, Edge, Neverflip, Weekland, and Clear for all your contributions, and hope to have some fun the last day. And to finish my keynote, I would like to thank everybody who have been helping in the organization as well as in the event for CTF, the competitions, and everything else. So thanks, Paula, for your incredible work and all the effort organizing all the speakers and all the events and schedule and website updates and Twitter updates and everything else. It's been a lot of crazy days in order to get this done, and I hope that everybody will be able to enjoy it. Also thanks for all the speakers, students, and so on. And also thanks to all the attendees, but you should remember that you have to follow some rules. There are some basic security measures that you should follow in order to be safe. So remember to wash your hands, don't get your keyboard dirty. Remember to use the mask. It's important to protect yourself from the face recognition software. You should keep the social distance. It's important for focusing, otherwise you won't be able to do anything. And we'll also learn how to code in the inner elbow. So it's a new skill that it's quite fun and important to do nowadays. And to finish, I would like to encourage you to use r2 and have fun. So let's begin.
Hey yo r2con, what's going on? I'm Banana Man and welcome to R2 Wars. You might remember my talk from r2con last year. I've had a talk regarding exploitation of Radar 2, and I've also got a blog where I'm writing about Radar 2, reverse engineering and exploitation. So before going into detail about R2 Wars, I have to talk about Core War first. It's a game where people write bots that compete against each other in a shared memory space. The goal is that you cause your enemy to perform an invalid instruction, which makes you the winner of the current round. It was released in 1984 and it runs in a separate environment that's called Mars, which means Memory Array Red Code Simulator. And you're writing your bots in red code, which is like a separate instruction set. Also, bots in Core can be multi-threaded, and there are all sorts of sophisticated strategies going on, and there are still ongoing tournaments today. In R2 Wars, we are writing our bots in x86, ARM, or MIPS assembly language. We have an arena that consists of 1 kilobyte of memory that's mapped as readable, writable, and executable. And also there's a separate allocation for the stack. In R2 Wars, you also have to cause your enemy to perform a crash, which can be done by corrupting the enemy's instruction pointer or causing it to read or write invalid memory, or causing it to trigger any other type of exception. R2 Wars was initially developed by Squatter and it runs in R2's easel environment. In R2 we can use easel to emulate code by using an intermediate language that can be represented as strings. If you want to know more about easel, you can watch a talk we had last year at r2con that's called Journey Through Easel. As a proof of concept, I'm showing this radar2 command that can be used to execute a bot's code in an easel environment. The important bits are initializing the easel environment and writing the bot's code into the memory space that has been allocated. For this, I'm allocating 1024 bytes using the malloc handler, and as a last thing, I'm initializing these values, which makes it possible to run a bot inside of the easel environment and to debug it. So that's basically what happens behind the scenes in R2 Wars, and you can also use this command to develop your own bots and to fix any bugs. In order to actually run R2 Wars itself, you have to get radar2 obviously, and you have to get the mono.NET runtime environment in case you're running on Linux. You're building the R2 Wars exe file from the C# project and just run R2 Wars from the command line, and then you can open your browser and go to the R2 Wars site that's running on localhost. This is what the game's interface looks like. We have 2 players and the arena in the middle, ranging from the address 0 to 0x400. You can observe the registers and the code that's executed by both bots. And if you check out the arrows on the top, you can see what it looks like in case player 1 or player 2 read or write memory. So for example, this is a run from last year using my bot on the left and another one on the right. And you can see both bots writing memory, and eventually my bot overrides the memory of the red bot, which causes my bot to win this round. These are the goals for the R2 Wars game. We wanted to create the nerdiest game ever, and you can also learn more about assembly language as you're developing your own bots, which is kind of a good thing. Also, you're having a lot of fun and you're winning beer, and you're getting eternal fame in case you're winning the competition. Also, we have a nice selection of Pancake's chiptune songs running in parallel, and another main goal is to find bugs in radar2 and easel along the way. Or we can also find bugs in R2 Wars itself. Please send money. As a general rule, you're sending in your bots as .asm files. Each Each bot will compete against each others in 1 versus 1, and your rank is based on the count of wins. Every day at r2con we will have one practice run, and on the last day of r2con we will have the final run where you can actually win prizes. Before going into detail in how to write bots actually, let me just say you have to make sure that your bots don't kill themselves and that they don't cause any timeouts. So for example, if you're having a bot that constantly writes stuff to the arena, you have to make sure that you're not overriding your own bot, because you have no way of winning if you're following this methodology. Regarding timeouts, we have a maximum of 2000 cycles, and after that there will be a new fresh round with new registers being initialized, and also the program counter and the stack pointer are getting randomized, so you have no idea where you actually are in the arena and what these registers actually contain. I/O and syscores are currently ignored by r2wars, so there's no point in sending in your reverse shell.asm file to Squatter. You can't hack him, he's unhackable. Another important thing is that the memory space doesn't wrap around. So if you have a bot that constantly reads or writes memory from address 0 to address 0x400, and you're not implementing any checks, the bot will read or write outside of the arena, which causes it to crash, and that's counted as a loss for you. The game is executed in cycles and in turns, so each bot gets one cycle and then it's the turn of your enemy. r2wars accounts for the cost for a given instruction, so if you're using instructions that require a lot of cycles, your bot will run slower. Also, you have to keep in mind that you're competing versus other architectures. So for example, your x86 bot will compete against ARM-based bots. And of course, each architecture has its own advantages and disadvantages. If you're not sure how to start, I suggest you're starting with an x86-32 based bot. But of course, if you're already familiar with, for example, ARM assembly, you can just use this. You will also compete versus various other strategies of your opponent, and in general, a good r2wars bot is a bot that works well against most of them. You don't have to fight each strategy in a highly optimized way. It just has to work against the majority of all bots. So now it's time to show some strategies and some tricks to pimp your bot. Most of the techniques are adapted from the Core War strategy guide that I am referencing at the end of my talk, and they distinguish between opening, mid-game and end-game strategies, which means that you can start using one strategy and switch to another one and then another one throughout your run. Of course, you can just come up with your own strategies, but keep in mind that there's no multi-threading in r2wars yet, so you can't use every strategy of the Core War strategy guide without adaptation. The most basic bot you can create is an imp, which executes the following stuff in a loop. It copies the current instruction to the next address, jumps to it, and does all that stuff all over again. It's basically built for survival, and it's not very sophisticated in that way. Another thing you can do is build a scanner, and a scanner searches for enemies in the arena, and as soon as it finds one, it just overrides this memory of an enemy. And in this listing you can find most basic and really bad example of a scanner. Please don't use it. And I'll tell you why you shouldn't use it in just a moment. Using this snippet, we can get the instruction pointer of our current bot in the arena, and we are executing this loop. It searches for bytes that are non-zero in the arena, and in case there's a non-zero byte, it overrides this byte using a return instruction. In r2ros, the arena is initialized using 0 bytes, so every other byte has to be from either yourself or the opponent. So let's check out a little demo for this. So let's just run this bot. It's now writing memory to the non-zero address it found, and it corrupted itself and it's dead. In order to fix this, I've changed the add instruction to add 10 instead of 1, which makes it scan from outside of our own code segment. But still, this bot really sucks, and I'll tell you why in just another demo. Now I'm running the fixed version of the scanner, and I'm letting it run for 1000 instructions. And you can see that it basically will get killed again because the value that's in EAX is way above the bounds of the arena. So there's a missing check for out of bounds. This is a fixed version of the previous scanner, which adds a wraparound for memory. So as soon as the EAX value is above 0x400, I'm moving the 0 value in it and basically start from the beginning of the arena. But still, this bot kind of sucks because after a wraparound, it just overrides itself and basically commits suicide. So that's a good example of what you have to keep in mind if you want to build a good bot. Here you can see an example of the two scanners fighting each other. I'm using the same one twice, and you can see they're finding the enemy in memory and overriding the memory space using a return instruction, which causes the enemy to perform a return and make it unable to perform any other attacks. As you saw on the previous animation, the enemy didn't crash, it just executed 0 bytes, which are in fact valid for x86. For ARM, this instruction is not valid. So you have to keep in mind which bytes you're actually writing into the enemy's memory, because you may actually write valid instructions which doesn't make it crash. Next, there's the bomber that writes bombs to random locations. Those bombs can be invalid instructions or instructions that cause an enemy to crash. You have to be aware that you don't kill yourself, because if you're really using random locations, you have to add a check to prevent bombing yourself. Since this bot doesn't move in memory, it's also an easy target, so it's maybe a better way to combine this strategy with another strategy that actually moves a bot in memory. The Core War players came up with a strategy that's called Vampire, and it involves writing jump instructions all over memory, and you basically capture an enemy by forcing it to jump into a memory location that's controlled by your bot. After capturing an enemy, it's the easiest way to wipe the controlled memory segment, but there may be more efficient ways to do this. This is a strategy that I've used last year. It's a bot that contains second stage code in its registers, and it basically pushes those registers to the arena, jumps to the pushed code, and does all that stuff in a loop. So you end up with a bot that moves in the arena and that writes a large amount of bytes per cycle. And of course, there's also the beer strategy, which is not really effective, but it's quite fun. Time for some random tips. As already said, it may be helpful to combine many strategies in one bot, so you will be able to fight various strategies at once. I also recommend testing your bot against real bots that entered the R2 Wars competition in the years before. You can find some of them in a GitHub repository that I've added to the references on my last slide. If you're an elite hacking dude, you can also search and find some exploits in R2 Wars like someone did in a previous edition, where someone escaped to the stack and wasn't executing code in the arena, but actually migrated all stuff to the stack, so there was no way to actually kill this bot. But obviously this was fixed later on. And keep in mind that r2con is a reversing conference, which means that people will go and try to reverse your bots like Anis did last year. He recorded runs and reconstructed the code of the opponents from his recordings, which is kind of clever. So now let's talk about tuning. You can see an example of why this is important. You're having two bots that compete in the arena and they're having a similar strategy. They're using the push AL x86 instruction to push code on the arena and then jump to it. So they're both replicators, but one is actually faster than the other, which makes it win. So if you're one cycle faster than your opponent, it may be an advantage. From my experience from last year, I can say that it seems to be important how many bytes you're writing per cycle. Of course, this applies to my replicator. In case you're using a different strategy, you may have to come up with a different metric. The different architectures provide different ways to perform push operations on the arena. And if you're using ARM, you can use the STM-IA instruction, which can be used to actually push more code in one cycle compared to the x86 push AL instruction. This may be an advantage in battles with bots that have a similar strategy compared to yours. You can check the cost of an instruction using the AO command. So for example, the push AL instruction takes one cycle, so you can use this instruction to further optimize your bot to make it use less cycles. Personally, I didn't count cycles for my bot. I've used something that I've called profiling. I'm using the same snippet that I've already shown before, but I'm adding this instruction to it, which makes the bot execute 150 instructions, and then I'm checking the content of the arena to see if I have any blind spots or if I have actually written more than before my optimizations were applied. This makes it easy to actually see how good your bot performs. Now, these are even more metrics Anis came up with. So for example, you have to count the cycles to the first write operation of your bot to measure how efficient or inefficient your initialization routine is. And also it may be helpful to optimize the length of a bot's main loop, so you can handle things as efficient as possible. So a few last things, how to actually participate. You should join the R2 Wars Telegram channel and send your bots in a Telegram direct message to this guy. He's also in the R2 Wars channel. And please follow the naming scheme. If you have an x8632 bot, you have to append this to the file name you're going to send. And for example, if you're using an ARM32 bot, you have to append this. So you have to name your bot properly, or bad things are going to happen. So that was it. Thanks for having me. If you have any questions, you can ask in the chat right now. You can also check out my slides that I'm publishing on my GitHub page. You can find some good blog posts and also some example bots and bots that Anis reverse engineered last year. You can also check out my blog post, which goes into detail regarding debugging, profiling, and actually writing a replicator bot. Moreover, there's the Core War strategy guide I've already talked about. It explains some basic strategies as well as combining some strategies to make a good bot. It also goes into detail on how to defeat certain strategies such as scanners or bombers. And lastly, there's this R2 Wars bots repository by Anis. You can find his blog post referenced in the bottom, and the top 5 competitors of last year are also present in this repository. I really recommend testing your bot against these bots because they performed well last year and they're using quite interesting strategies and combinations of strategies. He also goes into detail in his blog post regarding writing ARM-based R2 Wars bots. So if you're going that route, I recommend reading these blog posts as well. Peace out. Hey yo, r2con, what's going on? I'm Banana Man.
So this is the first round of the r2 Wars competition. You can see how the game is running right now behind me. The thing is that we will be running one round each day, and the final round will decide who is the winner. Well, basically the 3 first ones in the ranking will be the winners. So check out the current session and try to learn how the bots are running and how they behave, and which are the winners. So maybe yours is the winner one. This is the end of the first round. You can see that the three winners are Anis, Zattel, and Alkalinier. Congratulations to these three players. So hope to get some feedback from out of you from the R2Works channel. And get ready for the next round for tomorrow. So after this, we'll have like a break of 15 minutes, and at 18:30 we'll start the next talk, which is the workshop from Exploitable, Enovela, and Sule. See you later in 15 minutes.
А как вкусно. Ням-ням. Как вкусно, ням-ням-ням. Жу-жу-жу, а как вкусно, ням-ням-ням. Жу-жу-жу, а как вкусно, ням-ням-ням. Жу-жу-жу, а как вкусно, ням-ням-ням.
Okay, so testing. Can everyone hear me? Maybe you can write in the chat in YouTube if you can hear me. And we have reached the started scheduled time for the workshop, so we can go ahead and get started. And yeah, thank you for coming along. It's really good to have this many people joining us. We did this presentation or workshop last year at r2con. It was a full day, so 8 hours worth of training. And since we can't get together this year and enjoy r2con, we wanted to do something that was online. But due to the lack of online classes and things like that, we had to make it a little bit more beginner friendly and introductory content. So today we're going to talk about mobile reverse engineering, both Android and iOS. I'm joined by Alex and Eduardo, both regular attendees of r2con. So hopefully you should learn some things. If you attended last year, this might be more of a refresher for you, although we do have new challenges and things. But yeah, follow along and ask questions in the chat, and we'll try and answer them for you. So quick disclaimer. This is aimed at beginners to R2Frida. You might have experience with Radare, you might have experience with Frida, but you may not have used R2Frida in the past, or you might be quite new to it. And you may never have used it at all, which is fine, right? So today we're aiming to show you how to use the tool, how to get set up, what the different commands are. And we're going to run through a number of different challenges for you and show you how we would solve them and what commands we'd be using and why. And that way you could sort of follow along if you have devices and the applications installed. But if you don't have them, we are doing it as like a walkthrough, so you can follow along anyway. And of course, the YouTube video should be available afterwards. So if you need to go back and take a look once you have a device, you should be able to do that. So the main goal is really to introduce the r2frida tool, show you all the commands, get you set up and running, and then we're just going to jump straight into walkthrough sessions. So we've got 3 sessions for you today. So whether you're an iOS fan or you're an Android fan, there should be something for you. And even if you haven't really used these tools a lot, do stick around, because you should learn quite a bit, and at least the process and the experience of using the commands should tell you something that you can use going forward. So who are we? I'm going to briefly introduce the speakers because they're going to do their own part of this in just a little bit. But Alex is Alex Murphy. He's running the Capture the Flag for the past couple of years. He's a security researcher at Attack IQ, very mobile focused, and has used R2 and Frida and r2Frida quite a lot. In fact, the 3 of us all presented this workshop last year. Eduardo and I both work at NowSecure alongside Pancake and Ula and others. So we use tools like R2 and Frida quite a bit, and r2Frida especially. And yeah, together we're going to walk you through some examples of how r2Frida can make your mobile reversing much better. So the high-level agenda is going to be roughly 15 minutes of just introductions and showing you how to get set up and what the tools commands are. And then we're going to jump into Alex's session where he has some anti-jailbreaking and sort of crack me's that he's going to walk through, which will take about an hour, including a 15-minute break towards the end. And then we'll jump into the second session, which will also be iOS focused. And then we'll have another little break, and then we'll jump over to Eduardo, who will do the Android part. So overall, we have about 3 hours worth of walkthrough sessions using the tool, and a small introduction at the start. There's plenty of time for questions. We have allocated some time at the end. In the breaks, we'll be around to answer questions. It is a walkthrough. Unfortunately, it's not a classroom where we can stop and see every error that everyone's having and help you fix it. But we will do our best to answer the questions and help you fix anything that you're struggling with. But since it's an online event and it's aimed at beginners, we're going to have to treat it more like a walkthrough. But hopefully you can follow along, and everything should be explained nice and clear so that you can do that. We have some prerequisites that we'll get to, that you might have seen them in the Telegram or on Twitter earlier. But yeah, once you have them, you should be good to go. So the meme is back. Many people feel like they've got limited experience in R2 or limited experience in Frida, and quite often you find that people have experience of one or the other. And sometimes we use them both, and we might be very good at using them both. And some super smart people, a lot smarter than me, decided it would be really awesome if we could combine Frida and Radare so that we can leverage the power of both tools inside one like analysis tool. And this is something that was put together. It's available on GitHub at the Now Secure organization's GitHub. And you can go there and download it and start using it today. It is a little bit daunting if you've never used these things before, but as I said, hopefully throughout the sessions, you'll understand the commands and why they're used and when to use different commands versus other commands and so on. So don't worry if at the moment you feel like the person in the GIF. You know, it should, by the end of the session, you should feel a lot better about using R2Frida. So I don't think we need to spend a lot of time talking about Radare, but just a quick recap. It's been around for a long time. It's open source, sort of Libre tool. It has many different components within disassembler, debugger, decompiler. It does, you know, it acts as a hex editor. You can convert different types of data. Huge amount of functionality within R2, depending on your use case. There's generally always going to be something that you can make use of. It works on multiple platforms and architectures, whether it's Windows, Android, iOS, whatever it is that you're using, you can find a way to leverage R2. And one of the coolest things that I think we have around R2 is that the way you can extend it, right? It has a huge, rich set of APIs and bindings for different languages. And this allows things like R2Frida to come into existence in the form of plugins. And I think there's lots of different creative ways that we can actually make use of tools like R2 because of this. So R2 pipe is the de facto way that you would script R2 using various different languages, whether you're writing in Node.js or maybe you're writing in Python or many other languages. You can use R2 pipe to automate and script some analysis within R2. And they have a lot of extra stuff going on in R2 land now with Cooter, the graphical UI, and R2 Ghidra deck, the Ghidra decompiler that's now you know, present in R2. So there's lots of good reasons why, if you haven't really used R2 before, now is an awesome time to start. It has its own package manager, R2PM, which is going to be one of the ways that you can get access to and install R2Frida. And lastly, the event that we're attending, r2con, is an awesome conference. Last year was my first, but I'm super happy to be back, and kudos to everyone who helped put together a successful conference, even though it's difficult times right now. So that's awesome. Frida, another super popular tool. Hopefully you've had the pleasure of using it. It's a best-in-class dynamic instrumentation toolkit for analyzing processes live while they're running. So you can attach to applications and processes, you can inspect their memory, you can trace function arguments and function return calls and so on. It's scriptable, so there's a really rich and easy to consume JavaScript API, which is updated extremely regularly. So especially in the mobile space, we have a lot of attention here, and most mobile tools leverage Frida. So it's only natural that something like R2Frida would come into existence for mobile analysis. Like R2, it's multi-platform. You can run Frida in many different architectures and systems, and you can run it against apps in all of those systems as well. And as I said, it has a really rich API. If you haven't already used it, I'm sure you will at some point. And you can go to the website or GitHub, and you can find out more information. But we'll be using it today, so you'll at least get exposed to some of that. So as I said, some people had the idea that we could combine both tools. So why not write a R2 plugin that can drive Frida on the agent side connected to processes either maybe on your local machine or maybe on a mobile phone, for example. And we can actually benefit from all of the capabilities that we're used to inside Frida, but leverage the power of R2 as well to combine the analysis and include both static and dynamic capabilities. So using R2 Frida, once you have the plugin installed, you can attach to local or remote processes, just like you can with Frida. So you can connect to devices via USB or over the network TCP as well if you need to. And from there, you can use many of the commands in R2 that you're familiar with for converting data or printing data in different formats, searching across memory, or seeking to functions and disassembling them or opening them up in Ghidra, as we'll find out later on. But we can also interact with the Frida agent and consume and utilize all of the JavaScript API there as well. And that gives us access to far more capabilities than if we just opened it in Radare itself. So it's written in C and JavaScript. It's open source. As I said, it's on GitHub. You can download it from Git and install that way, or you can install it through r2pm. And it should install fairly easily, and you should be up and running. So how does it work? Well, on one end of the spectrum, we have Radare, which is the shell that will actually sit in, and all of the capabilities of R2 are present. We have the R2 Frida IO plugin, which is going to do, it's going to connect to the Frida agent within the target process. And we can leverage the plugin to run various different commands depending on our use case. Then we can leverage all of the existing commands in R2. So in R2 Frida, we have commands that can be interacted with using backslash, as we'll see over the next few slides. And like all R2 commands, you can include a question mark that will give you more information about the commands as well. So if you want to print the help message for R2 Frida, you can just put a backslash question mark, and it will give you some information. Before we get in, there are some references. The R2 Telegram, the Frida Telegram, the GitHub repos are all here. If you want to refer back to the slides later, I'm not going to go through all of them and explain what they are. But the point is, these projects have been around for a long time. They're getting better and better every day, not just every year, but every day. These projects add more features and more capabilities, and especially in the mobile space, which is of course where I'm working, we see huge benefits to using these tools for mobile security analysis. So do check them out if you haven't already. So there's some prerequisites which we uploaded to GitHub today. So there's some iOS apps and some Android applications as well. And it just lists out the prerequisites for you and points to all the GitHub repos. So you can go install R2 and Frida if you haven't already, and make sure you install the R2 Frida plugin. And you'll need to download and install the challenge files. And at the moment, it's preferred that you use rooted iOS or Android devices. On iOS, we're not able to do the challenges on the simulator, but on Android, you can use the emulator if you want to. And again, even if you don't have a device today, the video will remain online. If if at some point you want to come back and watch it again when you do have a device and follow through it that way, you'll still be able to do that. So first, we want to install R2 Frida. As we said, we can do that either from source or through r2pm. Both super easy to do, a couple of commands, and you should be good to go. And you can confirm that everything's working just by listing the plugins using R2-L, and you can see the Frida output for the relevant plugin, and that tells you that you have everything installed that you need. Once you've done that, you can use R2 with the Frida URL scheme to enumerate available USB devices. You can, if you choose a specific device identifier, maybe you have more than one connected, or if you use a double slash, you can just use the default device. But if you specify a device, you can also enumerate the processes that are running. So if you want to see, maybe you've got some apps open like Facebook or Twitter or something like that, and you want to see all the apps that are running, you can enumerate them using R2Frida. And assuming you have a target that you want to analyze, you can either do two things. You can spawn the app, which means the app isn't running already, and you want to start it up and be attached with an R2Frida session from the beginning, which is often the preferred option. And the other alternative is that you can attach R2Frida to an application or process that's already started. So you can use either spawn or attach, depending on your use case. And later on, we'll explain why you might want to do spawn versus attach, for example. So on iOS, there is a specific gotcha in that if you don't resume an application within 20 seconds of spawning it, I think it's 20 seconds. If you don't resume an application, the operating system can kill it because Apple takes the stance that if an application doesn't start up in a reasonable amount of time, then it's not a great user experience and it will be killed. So if we want to do analysis of an application and we're going to spend a bunch of time sort of reverse engineering it and figuring out how it works, then 20 seconds isn't really enough time. We can resume the app, but of course, as soon as you resume the app, it has the opportunity to start detecting you and altering its behavior and so on. So there is a URL here, if you need it, that has a super hacky script to just stop the operating system from killing the process. The disclaimer is it is hacky, and sometimes you need to kill Frida and restart the device. So use it as you need, but just take it with a pinch of salt. The other thing you can do, just like with Frida, you can connect over the network. So if you attended last year, you'll remember that we connected to devices over the network. So you can specify IP and port, and R2Frida will connect over TCP as well. So if you don't have devices connected via USB, you can always do that as well. So one of the key differences that you'll notice when you're using Frida versus R2Frida is that the underlying engine is different. So in Frida, for example, the default engine is duct tape, although you can override it. If you want to use the V8 engine, you can do so with some command line flags. But in R2Frida, the default engine is V8. And if you ever want to know inside Frida or R2Frida, you can use Frida's script.runtime, and you can check whether the engine is V8 or duct tape. And duct tape is quite useful in certain use cases if you're using Stalker or some of the other things that we'll show later on. If you want to change it in R2Frida, let's say for some reason you want to use duct tape, there is an environment variable as shown here that you can use to disable V8, and that allows you to go ahead and switch back to the duct tape engine. But it is something to be aware of because sometimes you can run into weird situations where code works in Frida but doesn't work in R2Frida or vice versa. So just as a sanity check, it is often good to check which runtime you're using, and that could be the thing that's messing up your code. So we have a number of different commands. We're going to quickly explain all of them. If you need the help message, you can use \. You can also do \V if you want to print out the Frida version. So here you can see in the JSON on the right-hand side, we're using 12.11.12, which was released yesterday, in fact. So like all R2 commands, we can leverage things that we're used to using, like grepping and case-insensitive grepping. We can parse JSON, or we can pretty print JSON. So we can make use of all of the R2 stuff when we're interacting with the plugin as well. You can also connect the session to the developer console inside Chrome. So you can do that in Frida as well, and also here in R2Frida with \D full stop. And then in the developer console, you can interact with the Frida agent. And this is nice when you're working with objects and arrays, because it allows you to sort of collapse them and dig into components within objects. So it's sometimes nice to just jump into the debug session in the browser and do that. But we're not going to use it for any of the sessions today. So in a similar way to R2, you have information commands that are prefixed with I. And if you want to list out the process info from the Frida agent side, you can use \I, which will give you some information about the running process. We can also run Frida code using \eval or even \space. Both of those will work if you want to run JavaScript code inside the target process. And if you mess up for whatever reason, as you'll see many times today, you'll accidentally mess up the program, or maybe the program will detect you and you have to restart it. You can simply use OO, and it will restart the app, and you'll be back to the beginning again. So that's quite useful. So for information commands, I'm just going to bring them all on the screen. In the similar way inside R2, we have a way to get access to imports, symbols, the library lists, exports, the entry point. All of these things can be obtained from the remote process, so that we can pull them into R2 and leverage them. So we can find out which classes and symbols are present inside the app. We can go and find the addresses of all the functions. We can seek there. We can disassemble them and analyze those functions, just like we would statically using R2. In both Android and iOS, you can use \IC, which will give you information on the classes. So you can see all of the Objective-C classes or the Java classes that might be inside the app. You can grep, just as you can with other commands. You can grep or do case-insensitive grep. Let's say you're looking for jailbreak detection, or maybe you're looking for root detection. You can perhaps find classes with those names. You can also pass a class name itself to \IC, and that will give you information on the class. So if you want to find the functions that belong to that class and any of the methods and their addresses, you can do that as well. And then one of the more important things that we'll be leveraging today is the dynamic tracing capabilities inside R2Frida. So there's a huge number of different ways that we can interact with R2Frida, including leveraging Frida's interceptor API. And we can trace functions and tell R2Frida how we'd like to see the arguments. So maybe they're decimal values, or maybe they're pointers or strings or Objective-C objects. They can be many different things. So this gives us a really quick way via commands to trace functions and view the outputs in different formats. We can also trace registers. So working on ARM64, we want to trace different registers, maybe for arguments or for other different reasons. But in this example here on the right, we're going to do a trace of the fopen function. So we can print out the value of x0 whenever that function is called. So you'll notice the backticks in this example. Backticks are a way in R2 to chain commands together. So we can run \ISA fopen, which will just return the address of fopen, and we can feed that output into the \DTR command so that we can script it and automate it much faster. We can also set breakpoints and remove breakpoints. We can pause at certain points in the app and inspect things. So maybe not just with Frida, but we might want to stop at certain points and inspect what's happening, maybe in some cryptography routines, or maybe there's some anti-jailbreak or anti-Frida or something that we need to circumvent. If we can find it, we can put some breakpoints there, inspect the memory, and sort of step through each part. So there's lots of useful commands under \DB. And again, if you want more info on them, you can just put a question mark and it should give you some details about how you use them. And here, for example, we can list the registers, and like most commands in R2, or not most commands, but lots of commands in R2, you can append a J at the end of the command if you want to get it in JSON format. And using braces, curled braces, and the tilde symbol, you can actually parse the JSON as well. So there's some really cool ways in R2 to dig into the JSON and pull out the parts that you want. So in the bottom example, we're pulling out the program counter. So the J flags to get JSON output can be really useful, especially if you're scripting or writing things with R2 pipe. Maybe you're automating some bypasses in the app. Maybe you need to hook things and bypass things in a very quick way. So using R2 Frida through something like R2 pipe can be a really awesome way to do that. You can also list out all the memory regions for the process, which we'll be doing later on. So you can see the memory ranges, the memory maps. You can also interact with the heap. So you can allocate blocks of memory. You can allocate strings on the heap. You can deallocate memory. So there's some nice wrapper commands that facilitate those kind of use cases. And again, in some of the challenges today, we'll actually be using them. So as I said, huge amounts of commands that are available for you. All of the standard searching capabilities that you might make use of, maybe you're searching for strings or searching for hex pairs, opcodes or something like that, we can also do that inside R2 Frida. And we have this nice convenience command, \e/, which will basically set all the search variables to the place that we're currently looking in. And so let's say we're looking in an app and we want to find a certain pattern or signature. We can search just within that app and maybe not include standard libraries, for example. So we can actually narrow down the things that we're looking at. And in general, with \E, you can see the various variables and parameters that you've got configured inside R2. So maybe you want to alter the behavior of Stalker, or maybe you don't want backtrace outputs, or for both outputs, you can change these via variables. You also have commands to interact with the file system. So you have mount commands where, let's say you want to mount the device and you want to sort of browse through the Android file system. You can use MC to read remote files. You can also write to remote files on the device. You can drop into like a little mini shell and browse the files and directories as well. So there's commands under M where we can go ahead and interact with the device to save you sort of tabbing out and using SSH and SCP and other things. So be sure to check them out as well. And then one of the key ones that's hidden away in the usage info is \init, which basically pulls in some variables, and from Frida it obtains the entry point and libraries and imports them into R2. It then mounts the device for you and then seeks to the entry point of the binary. So basically, you can just get up and running. Essentially, if you run \init, it will print out the commands and you can see what this thing is going to do. But if you actually want to run the commands, you can just put a full stop in front of it, just like shown here on the right-hand side. And you can see that we get a message saying that we've mounted IO at /r2f, and you can see that the currently seeked address has gone from offset 0 to 104, blah, blah, blah. So in this case, we can actually run that. So it's usually one of the first things that we'll do when we get attached to a process. So that's pretty much the introductions. We are now going to jump over to Alex, who's going to start the first iOS walkthrough. Hopefully you've had a chance to install the apps. As I said before, it's going to be extremely difficult for us to stop and start all the time and make sure every single person's following along, but hopefully you find it easy enough to follow along. And worst case scenario, you can always go back through the video. But with that, I'm going to hand back over to Alex, and he can introduce himself and start his session.
Okay, everyone, can you hear me well?
We can hear you, or I can hear you.
Okay. Perfect. Hello, everyone. I'm just a walkthrough around iOS. So in that case, what we are just doing is just a little intro in Objective-C using r2con2020 commands, just to apply what Grant explained just before. And we are going to just make some little crackness applying r2con2020 to an iOS environment. Just especially focus on just bypassing the book checks and bypassing jailbreak detections. Some basic checks that are quite often in the applications, and just how to use r2con2020 just to bypass them. So just to going through the session, some things to remember. First of all, just remember to use Radar2 from Git, to use the last version. So in my case, for example, the last version they have is just the 4.6.0. And just use the last version of, as Grant said, 12.11.12, but it's the one stable, the last version, and just update it to r2con2020 using the r2pm commands. That if you have already an r2con2020 installed in your computer, just the good way to do that, it's just clicking that command, because you're going to clean the old version and just install the new one. So it's just the good way to update that to r2con2020 to the last version. So in that case, here in the right, you can see my phone that is just upgraded. We can see here which version we are using now. Yes, the 13.11.1. And we have already as well r2con2020 installed using Cydia, because this iPhone is a jailbroken iPhone. So we in that case, you can, the best option and the easiest way to do that is just use Cydia to install r2con2020 in your phone. That's all from our side, to just have a good environment just to follow this walkthrough using iOS applications. Okay, so let's go start then. Just the beginning, what I'm going to do is just use r2con2020 using the option U in uppercase, just to see which applications I have installed in my mobile phone. In that case, we are going to use two applications. The first one, just to see a walkthrough in r2con2020 commands, just an easy way to see how to apply what Grant just explained before. And what we are going to do is just trying to solve the iOS challenge too, that it's a little challenge that I made by myself. So just as Grant said, just to use r2con2020, we are going to just use the command r2, just using the r2con2020. And what we are going to do now is just spawn a process using our USB, and we are going to spawn this application. This is the bundle ID that we can see it using the r2con2020 command previously shown. So in that case, start, and it's paused because it's just waiting to add to Frida just to continue the process. And that's it. So we have now the application up and running, and with add to Frida just attached to the application. So just something that we are going to do during the whole walkthrough during iOS, just remember to disable this option. Is our analysis of the applications. And here, just we can start now. What's the first thing that we can do? The first thing is just we are going to see which classes have this application. In that case, we are going to use the command IC, just prevent it with the slash, just to use an add to Frida command in that case. And here we have all the classes that this application has implemented on it. Just because it's quite verbose, this command, this option is just to by, for example, which view controllers you have using the stick here. And here we can see the main view controller that it's called view controller. So in that case, what we are going to do is just to show which functions are implemented into this view controller that it's called view controller. So just to analyze the functions, for example, we are going to analyze the function just that we suppose that it's just attached to this button, that it seems that to be this one. And a good option to reference that, what we can do is just select the memory and just move to this part of memory of the process. Or another more elegant way to do that is just what we can do is just execute this command, create without the dot first, just to create the flags into the process. And if we prepend it with the dot at the beginning, just we load all the information into our radar session now. So now we can just to view controller and the method called button click in that case. So the second thing that we are going to do is just import or get all the input of the process into our session. That's the best way to do that. And just we are going to analyze the function. So let's go and see what's going on here. You can see just all the disassembly, some constant strings just right here. The functions are not resolved. So the best way just to solve this option, for example, is just we are going into this function, for example. This function, it's just a reference to Objective-C message send method, that it's an Objective-C method used to make Objective-C calls into the application. And what we are going to do now is just rename the function, this name, with the command that it's called afna. It's .afna. And just we can see in the disassembly just the function that we previously shown was renamed. So now it's getting better. And we are going to do the same with the method, with the other method to rename. So in that case, we have now just more references in our method. However, what we don't have are the references to NS strings. That what we are going to do now is just we are going to use a net2frida plugin that it's called CF String. You have the code into the GitHub where you can find the application and you can find the code as well. So if you see the GitHub, just here in the folder that calls plugins, you're going to find out the code that we are going to use now. It's called cfstring.js. So this is the code of an r2frida plugin that you can see the code if you want it. Just right here. I'm not going to go through the whole process, but what this script is doing is just memory process looking for references to NS strings and just parse the structure and add them as flags into the r2frida session. So we are going to just load this plugin as using this command that is just with the slash and a dot at the beginning and just the path to the script. And this script, what it does is just creates a new r2frida command that it's called with the star at the end, just to create all the references to the code. We using the flag format R. So then a dot at the beginning. All this information has been added now. And we are going to analyze again the function. And let's see what's the difference now. So here we can see references that it's a selector, just the method name that it's a parameter that it's need in the Objective-C message send function called, just to create the function calls for Objective-C in that case. And here, for example, we can see that what this challenge is doing is just comparing two strings using the is equal to string method that is an Objective-C method from NSS string. And if it's success, it's just using the string you found the secret, and if not, just is using this string it's not you are looking for. Showing the pop-up. So that's a good way to start, because we are analyzing the function in memory using r2frida. So we are disassembling and analyzing all the objects and all the instructions directly in memory using r2frida in that case. Just something powerful that we can do as well with r2frida is just with eval. With prevented with eval, we can execute frida commands. So we can just put in frida code in line here. In that case, just as an example, what we're just doing is just showing all the layout of the application, of the Objective-C application, where we can see, for example, the labels, the text fields, the buttons that are inside the application. And here we can see the secret, for example, that it's what it is expecting the application. This is the UI label that it's given, so we cannot see it in the main application. However, it's there. So, well, I guess you don't have any question. So let's go ahead to the next challenge. That is what we are going to do now. In that case, I'm just closing the application and trying to open it again, that is the iOS challenge 2, which is what we are going to do now. So if we try just to execute the application just crashes. That's typical sign that it's doing some checkings. And if it detects, for example, that it's just executed in a jailbroken device or just using some debug features or capabilities, just crashes the whole application at the beginning. So that's the main reason why with r2frida, what we can do is just prevent it at the beginning without executing any application code, and that's a good way to bypass that kind of things using r2frida. So let's execute the application. Just changing the bundle ID. Just typo. And the application it's waiting for our r2frida commands until we just continue. If we continue the application, okay, it crashes as we expected. So we are going to see which kind of checks is doing and where are implemented those checks. In that case, what we're going to do now is just the first thing to test is just if the application is just to ptrace application, because with ptrace we can just calling a ptrace, we can just deny the execution of ptrace. So it's a basic way to the application is being debugged or not. So what we are just doing is just reboot the application again. Use the command ttf. Well, just to trace if the ptrace is called or not during the beginning of the execution of the application. So DTF, what it does is, if you remember, we are tracing the function, and with the F at the end, we can just tell to r2frida the format, just to format the arguments. In that case, the 4 arguments are integers, and here we can see that ptrace it's executed at the beginning of the application running with at the beginning with the first argument. This argument, the 31, it's the deny ptrace option. So the application is just not allowing the use of ptrace into the application. Just what we are going to do now is just we are going to just analyze the application in static, just to see if we can find the ptrace call, and just to identify where the code is implemented, just reverse it and just use r2frida to just bypass all the checks to allow the application just to run. So just to execute the application, we have the IPA that, if you don't know, it's just a zip file. So if you just extract the IPA, just it gets a folder that it's called payload, and inside payload you can find the macro, that it's the binary file that the iPhone is executing. So in that case, we have analyzed the application, and we are going to look for references to just DL stream. Why DLSim? It's because it's a function that it's normally used to identify the ptrace call and just to get the pointer to the ptrace function and just to call it afterwards. In that case, we have a reference found in that symbol, just moving forward there. And there we go. We have the DLSim here. And here we have the string ptrace that is what it's using in DLSim. So in that case, this function it's just calling ptrace using the argument 31 that it's just right here. This method it's called by the method called view.load, but it's the first method executed when a view controller, when the view is just load, and it belongs to a class that is called challenge1. We are going to use the IC command without the slash at the beginning. The methods here, just right here, and just if we select the address, just to move to the method implementation. Here, all the implementation of the checks that the application is just doing to avoid to being executed or being debugged. In that case, we can see two checks that if they are not correct, they are going to this block that is just telling us that the app is being debugged. And we have another check that is just avoiding if the application is tampered or not. So let's move on through the different checks and just trying to bypass them one by one. The first thing that we are going to check is just function that it's calling get pipit, that it's another typical anti-debugging check, which is easy to bypass, but well, it works. That what is checking is that the parent process it's not one. It's the process that is the normal process that it launches all the applications in iOS. In that case, if it's not one, it's just just return that the application is being debugged in that case. So we are going to just rename the function just to easy the analysis. And here we have the check, the pipit. And just analyze as well this one. Sorry that I forget this one as well. That it's the ptrace one. In that case, we're going to rename it just to get it. Yeah. So we have here the ptrace call here inside that function, and just checking the pipit, just the parent process. So just we are going to first of all bypass the ptrace. How it's possible to bypass the ptrace? Here I have some references to the OWASP where we can see those kind of checks. In here you can just see the code that is used for just the ptrace. And here we have that the ptrace in I attach, it's the number 31, that is the one that is in the application. What we have to do is just modify this value with just -1, just to disable that call and just to avoid that the application is just denying to attach the process. The first thing that we are going to do is just in r2frida, you can just modify modify the arguments of a function using Frida commands, just using the interceptor, for example. But what we are going to use is just we implemented a little r2frida plugin that is doing that for us. Just you have the code as well into the GitHub. However, I'm going just to show a little bit the code just to see how a r2frida plugin looks like, and just to see that it's not so difficult to implement new r2frida plugins by yourself. In that case, well, it's just a basic plugin, and we are just adding those new commands that it's DAY1 with a 0, with a 1, or a -1, depending on if what we want to modify the first argument of the function is with a 0, with a 1, or with a -1. And in that case, what the method is just doing is just calling the interceptor attach method, just intercepting the on enter of the target, that it's just the function pointer that we use in that call. So let's go just to get the plugin and just okay, application just crashed. Just okay, the application crashed in some way because there's more checks that we need just to bypass first. However, the plugin was executed just over purchase, and just what we are just doing is just modifying the original argument that it's just 31 to the -1. And the only thing that we did just was loading the r2frida plugin and just using this command just to modify the first argument of bitrace. So it's an easiest way to just bypass bitrace detections in your iOS applications in that case. So if you remember, there is another command that it's called DAY that it's doing kind of the same that the my r2frida plugin, however, with the return value that it's just intercepting the function and just returning 0, 1, or -1, depending on the call that you use, and you need to send the function pointer that you want to intercept in that case. So just to hook the get parent process bit function call, make it returning 1 all the time. It doesn't matter if it's just a debugger attached or not. The best way to do that is just using the command DI with a 1 at the end, and just the symbol get repeat with the symbol that we're using in that case. So with these two options, but what we are going to do now is just get some just to remember all the commands that we are just executing. We already bypassed bitrace with this. We already bypassed the get repeat option. And we are going to check doing else. So we bypass this check. It's the trace, they get repeat well, and just we need to check this option too, that it's just going to this branch as well. So this option is just, if you see here the symbol, it's just telling you that it's another typical way to identify if you have a debugger attached in your process from iOS, that it's just using CCTL, good way to identify, to get the information of the process and just check one specific flag to identify if the process is being debugged or not. So in that case, there's many ways to just bypass this kind of checks. You can do it using a Frida script that we can just see here and just have I'm just going to show you the Frida script to bypass the CCTL check. Only Frida if you want, and you can just, with that to Frida, you can load this script and all the checks are automatically bypassed. So it's not a problem. However, there's other ways to do that. In that case, what we're going to do is just, we are going to override the call to CCTL, and with just to avoid this call. How we are going to do that is just, in that case, let me spawn the process again, and we are going to find out the function pointer, and just what we're going to see now, just in that pointer, just override with a return value in that position. So just to this is what we are doing here, that it's just getting the function pointer to disassembly to instructions, and then just write a return value into the position that we see before. And just to avoid being so verbose with the anti-debug checks, the last one, it's quite easy to bypass. It's just this one, that it's just detecting if the application is tampered or not. And what it's doing is just looking into the libraries, load into memory, just to check if some of them is Substrate, Cycrypt, SSL kill switch, or even Frida or not. And how is checking that? We can see here that it's just checking for substrings. So it's just iterating all the names, all the library names, and just iterating over there if it's possible to identify any of those names. So there is usually a way to just bypass that with to Frida. It's just making the function str return 0 all the time. It doesn't matter if it matches or not the string. So in that case, we are going to just test our script. don't remember how I called the script. How the code was just overwritten. And if we call this C, and we continue the process, we can see that all the checks that it was doing at the beginning, the application just were bypassed easily. So just if we want to just reproduce the example doing the code that we have shown before, it's just the same. So with r2frida, you can solve the problems in many ways. You can use just Frida scripts as you maybe used to do, or you can just use r2frida commands that it's just like a mix between radar and Frida. But with r2frida, as you can see, there's so many ways to solve the same problem, and just quite easily, as you can see. So here we have the application that is just having 3 stages. You click check, it's just getting that the device is jailbroken. So, well, let's start the analysis as we did with the first application, just disabling the no skip option of the analysis. And just here, if we see the classes and filtering by challenge, we can see that we have 3 classes. Each one is just assigned to one of these views that we can see here. We are going to start with the challenge 1. And we are going to load all the symbols into the r2frida session. And just to check which method we have the method jailbreak test 1 tab, that it's just this check, and another method that it's called is jailbroken. So let's go to this method. Here in r2frida, there's some options to move through the methods that we are going to see now in a moment. So just be sure that all the imports are already just loaded. Going to load our plugin just to get all the strings. Analyze application and just see what this method is doing. So as you can see, it's just a short method because what it's just doing is just calling here, just rename the function. What it's doing is just calling a message sent with the method is jailbroken, and it's another method into the class that we've seen before. And it, depending on this result, it's just getting if the device is jailbroken or is not jailbroken. So this method, we just check this one is just returning true or false if the device where the application is just running is jailbroken or not. In that case, sorry, I forget to analyze the application. So here you can find all the checks just implemented. That is just checking if you have Cydia installed in your phone, or if you have mobile substrate, you have WinBash or the SSH installed. It's just checking for files into your phone, just specific files for specific jailbreaks of your phone. Or another typical thing is just trying to access to a Cydia URL and if it's possible, so it says that the device is jailbroken, but it's not. So all these checks are implemented here, and what the method it's just doing is just returning 1 or 0, depending. So true or false, depending on the checks, how have been doing. In that case, it's quite easy to bypass this check, because just if we know that there's a method that it's returning true or false, depending on if the device is jailbroken or not, something that we can do is just replace the call. So we can do this in 2 different ways, as I said before. The first one is just calling DAY0 and just using the address of the call. So in that case, all the calls done are going to return 0. However, there's another better option. I prefer that it's just using this syntax. In that case, just all the calls made to the jailbroken method are going to return 0. So 0 is false. In that case, we're going to check, and voila, the device is not jailbroken with only just check, as we have seen here. So the first stage, it's quite easy, as you see. Let's move to the second stage. That you're going to just add it all the symbols of the challenge tool. That let me just show you which methods are implemented. I quite the same. The jailbroken and the test2 tab. We can move first to the jailbroken method. Let me analyze the function. And this method is just doing nothing, because it's just returning true all the time. So maybe it's just some fake function that it's implemented into the application. Maybe we need to move to another function. That it's in that case, it's challenge2, and this method that it's the one assigned to the button. And let's see. I'm going to just, to be sure that all the strings are already loaded, I'm going to analyze the method. And here we can see more logic. So it seems that all the jailbreak checks are implemented into that function. Here we can see that, yeah, it's possible, because we can see that we can see a string that is just checking if the string of if it's possible to make a request to a CDA handler, that it's just r2con /read.murphy.jailbreak. However, we see if the device is jailbroken or not here. However, we cannot see the strings into our paths. So we don't know which paths we are checking in that case. We know that we are checking some files into a file system because of the selector that we can see here, and it's just passed to the end function, but we cannot see which paths are used. So it means that maybe it's not possible to analyze statically as we did in the last challenge. However, if you remember, we have the option of tracing using i2frida. So let's play with it and just to see which paths are already used in. So in that case, we are going to use DTF. And using DTF, we need to just define as the first argument the pointer to the function. In that case, is a function that it's called fileExist.path that it's implemented into NSS file manager. It's a core function typically used in Objective-C. And just how to reference that with r2frida is just using something like this, where you have here the class name, it's NSS file manager, and the method name. In that case, we are going to trace on the enter instead of the exit, just using the tick. The first argument is just a pointer to the instance that it's going to make the call. It's an instance to NSS file manager. And a string that is the selector that it's going to show us that its file exists at path, and an object. So let's just execute. The device is jailbroken, and we can see just right here, we can see all the references just that are all the paths that we are just checking in this jailbreak detection. We can see, for example, mobile substrate as well here, and so on. So best option to just bypass that is just using DI as we did previously. In that case, with that, we are returning all the time false. So any file exists in our application now, using at least that like function call. And just to bypass the other check, something that the other check, if you remember, is just calling a URL using a method that it's called can_open_URL. First of all, we are going to identify where it's implemented, just to check it. So a good way to do that with Frida code is just using this function that it enumerates all the matches. And just here, we are just looking for the function name that's called can_open_URL. And we have two occurrences, but the typical one is just this one that it's in the UI application. So we are just the same, so just intercepting the function, return value, and returning 0 all the time. So I'm just doing with those simple steps. The device is not jailbroken anymore. So just to finish, in my case, it's just, as you guessed, the strings in the function were obfuscated. So they are not in clear text in the application, so it's not possible to see them. However, if you analyze deeply the application in that case, you can see it's called reveal, that it's doing something that using what we did, the same that we did with the can_open_URL function. We can try to identify if there's a class implementing this method in our application. So we have the application obfuscator, that it's called reveals, that it's just decrypting the content of our application in that case, and just with a small Frida script that I'm going to just copy and paste just to avoid any typo. But it's just using interceptor to use the obfuscator class name. In that case, just to get the pointer. That's an easy way to do it in R2 Frida. It's just getting the name, just filtering by the function call, and just getting only the first column. There we go. We have the same. This is the address implementing that method. In that case, now we are intercepting the function, the red value of the function. So that's because let me just disabled all the traces just to avoid being too much verbose. Here we have all the paths that the application is just checking to detect if it's jailbroken or not, the device. So that's it from my side. Uploaded into our GitHub. You have another level that I just leave you for homework. That is just kind of doing the same with some different tricks, more complicated, that just intersecting one function call. Just so I hope that you had fun and play with R2 Frida. That as you can see, it's quite easy if you know what you're doing. So thank you. We are going to have a break, as far as I remember. It's like a 15 minutes break. And let's continue with the Android part, with the iOS part, sorry.
Yep. Hey, well done, Alex. Yeah, I think Pancake's going to throw on some music, and we can take 10 minutes and just grab a coffee and then get started with walkthrough 2. Hey, welcome back. So we're gonna go ahead and get started. Hopefully everyone managed to grab coffee and use the restroom and so on. Just checking everyone can see the screen. It's appearing on the YouTube stream. Looks like we're good to go. So yeah, we're gonna carry on with iOS, and we are going to look at a CrackMe that was put together for last year and has been modified and updated with some extra sets of challenges for this year. So I'm going to tab out, and in a similar setup and format to Alex, we have the device over here on the right-hand side of the screen. You can see sort of wiggle the springboard. So we have this CrackMe app that if we go ahead and run it, you'll see that it just runs for 2 seconds and then decides to crash itself in suicide. So part of the challenge is to try and figure out what's going on, why is it doing this, and how can we circumvent this. And crashing the app or blocking the user is a really typical behavior of common protection products, right? So when you see applications that have jailbreak detections or root detections, FreeDA detections, and this kind of stuff, quite often they'll react in aggressive ways, often crashing the app completely. So this is meant to kind of emulate that, I guess. So if I run it again, you'll see it just goes ahead and dies. So just like we did before in the first session, we're going to spawn with r2frida. And of course, if we resume with DC, the application will just die. We can, of course, spawn the app and begin our analysis. But as I mentioned before, on iOS, after about 15 or 20 seconds or something, the operating system's going to kick in and kill it. So that's going to give us a bit of difficulties if we want to analyze the binary, right? So what we can do is we can run this script that I put in the slides with the QR code. Here is the URL for the gist, and you can see how to run it up here in the comment. You just need to have the application's bundle ID. So again, the disclaimer here is that there's no warranties or any liability with this script. You might have to reboot and get into weird states. Unfortunately, it is very hacky, but it works for us, and I trust it since I wrote it. So we're going to connect with USB for FreeDA. We're going to connect to the Springboard process, which is the sort of menu that you can see here on the screen. And we're going to pass in the JavaScript file. And all that's going to happen now is if we reboot or restart the application, what we should see this time is that after 15 seconds or 20 seconds or whatever that timer looks like, we'll see some activity in this FreeDA tab that just tries to prevent us from getting blocked. So if we give it a few seconds, there we go. So we see the console logs to say there was a watchdog provision violated and our app was trying to be terminated. But as you can see on the screen over here on the right, we still have the application running. So that allows us to continue our analysis without worrying about the operating system going to kill us after a few seconds. So we can spend as much time as we need. The application doesn't have a chance to run any code or detect us or crash yet because we haven't unpaused it. So here, like we did with Alex, we can, we can run our init command, seek to the entry point. We can list, let's say we want to run some code on the FreeDA side. We can check the runtime. We can call other parts of the FreeDA API like process.arch, and we get ARM64 back since I'm using an ARM64 device. You can also do clever things like, let's say we want to say event equals r2con2020, and we want to say console.log hello from event. We can run JavaScript on the agent side, and you can see the application and the agent is very much alive, even though the operating system should have killed us a long time ago. So this can be quite useful if if the application is behaving in an aggressive way, and you need to spend a bit of time figuring out what's actually going on here. So I'm just going to clear the screen. Maybe make it. Maybe I can make it a little bit bigger, so that everyone can see it properly. And we can do things like list the libraries. the application is called CrackMe, so we can search for that and we can see the CrackMe is located there in memory. We can also list the imports and symbols and things like that. We can also list all of the classes just like Alex showed. So here from Frida, we can get all of the Objective-C classes that are in memory. And all of these things, we can choose to import it in R2 format. So if you put an asterisk, you can see we get it in the flag format that R2 expects. And we can just import that with the dot. We can go ahead and get the exports, symbols, and we'll pull in the libraries as well, even though our init actually did this for us. So we can pull in that information, and now, for example, if we want to seek somewhere, we can use the symbols. So let's say, go to nslog, for example, and we can print out an instruction there. So now we've pulled in information from Frida that's going to help with our analysis, right? So we're actually seeing where these things are at runtime. So we can also do things like we showed before, where we might want to get the Frida version, or maybe you want to pretty print the JSON. If in some commands you might want to parse that and do other funky things with it. We can also go through and look at the classes, just like Alex showed, to see like what it is that we want to inspect here. And like he did, we're going to look for our view controllers. Now I already know the name. It's the first view controller. So we're going to go ahead and look at that one. And just like before, if you want to, you can pass the class name to \ic, and you can print out the methods and their addresses for the given class. And if you want, you can also do this in R2 format, and as we did before, we can import it in R2 format. So we can actually seek to any of these symbols now that we have them inside R2, and we get tab completion and other nice benefits for doing that. So I'm going to go ahead and seek to the viewDidLoad function, try and figure out what's happening when the screen appears. And to do that, I'm going to quickly turn off anal.nopskip. And we are going to seek, actually, did we seek already? Yeah. So we're just going to analyze the function, and then we'll take a look at what might be happening here. So it should take a couple of seconds, nothing too much. So let's see. Give it a few seconds. While we do that, we can talk a little bit about how we're going to approach the challenge. So we're going to have to solve challenge 1, which will unlock access to challenge 2. And there's like a stepping point between the two challenges as well, like a little mini bonus challenge that we're going to have to think about and solve. So okay, we've seeked to the function, we've analyzed it. Let's go out and let's print maybe like 50 instructions. So here we can see a number of different things that are happening. We can see calls to Objective-C message send from the Objective-C runtime. We can see things for the stack check guard. We can maybe print out a little more. We can print out the entire disassembly for the function. Shouldn't take too long. There's no obfuscation in this app. We have used macros and function inlining just to make things a little bit more challenging. So the function size is a little larger than you typically see in a normal app, but again, it shouldn't really take too long. And in fact, we can probably just print out the output early by Control-C. So really, what's interesting here is we can see there's a bunch of XOR instructions, which could be interesting. Just scrolling through it, we see these tend to repeat quite often. And there's also a recurring pattern of calls to the DLSim API and memcopy. And if we keep scrolling, we'll continuously see the same pattern repeating over and over and over again. So that could be useful to look at. Again, memcopy. Up above, we should also see calls to DLSim. So what we want to do is we want to go ahead and analyze what this might be doing. And DLSim is of particular interest. If you aren't aware of the function, we can run shell commands with the exclamation mark, and we can get the man pages for DLSim. So DLSim is a function that allows you to resolve at runtime the location of a symbol. And so essentially what you want to do is pass in a string of the function name you're looking for, and DLSim will try and resolve it for you and give you the address. And this is quite common in iOS and Android apps to conceal the APIs that you're invoking. You obscure that behind calls to DLSim. So you might look up the addresses of, let's say, socket, read, write, fopen, access, all of the APIs you might use to detect tampering or detect that the device is jailbroken. You can look them up using DLSim, and then you can invoke them using the function pointer rather than using the import directly, just so that when people are reviewing the app statically, it's not always completely clear what's happening. So DLSim calls are definitely going to be something that we want to check out and have a look at, especially because it seems to be a recurring pattern inside this application. So we can go ahead and look at that. Since we imported the symbols, we can actually, if I seek back to the entry point, we can see in our symbol list DLSim and others. We can also use IAS to look up the address of a symbol. So we can ask to get the live location of DLSim. And using that, we can trace it. So if, for example, just to demonstrate, I'm going to print out 2 instructions at that location. So here you can see 2 instructions at DLSim. And like I showed before, you can chain commands with backticks. So if you wanted, you can put /IAS DLSim in there, and you get the same output. So it depends on what you're doing. You might want to chain different commands if you're trying to interact with the process and do things quickly. So we can use the D commands. There's various things for tracing and interacting with memory and breakpoints. For this example, what we're going to use is DT. So the dynamic trace functions, there's various ones. Some use stalker, some can trace and print register values, others we can pass format specifiers. And in this particular case, we're going to use /DTR. And if we quickly look at the DLSim man page again, the first argument is the handle, and the second argument is the string that represents the API we're looking up. So we can actually look for argument 2, and that way we can print out the value. So in ARM64, the second argument is going to be in the register X1. X0 would hold the first argument, so we'll be looking at X1 because we want the second argument. So to do that, we can do /DTR, and then we can pass DLSim, and then we can just say we want to hook X1. And I'm just going to clear the console because there's going to be a lot of output, and I'll explain why that's important in a second. So now that we've set up a trace on DLSim, we want to resume the process using DC, and we'll see a large chunk of output. So I'm just going to go ahead and copy all of that, and we're going to jump into VS Code and process this. So I'm just going to clean up the JSON a little bit to get rid of the r2 commands. And we'll just call that output.json. And so if this was like an interactive command that we were using and wasn't an async output, we could, we could actually just go ahead and interact with the output and parse the JSON directly in R2. But I'm going to step out to the command line and use JQ. But you could use anything really if you feel up to it. So with JQ, we can print the JSON. There's a lot of information to digest, but really all we care about is the values field. And specifically, there's an X1 entry in there because that's the register we're printing out. So with JQ, you can actually say, I want the values field, and then within that, I want X1. And we'll print out only those things from the JSON. And better yet, we can actually go ahead and clean this up a bit with some command line kung fu. So we'll just say we want the second argument, and we want to sort it and get it unique as well. So here we can see all of the symbols that are being resolved by the process. Some of these are legitimately happening throughout the app and the various libraries that are present. Some of them will be by the code that's detecting us. So here we can see LSTAT, which is definitely eye-catching. We see a lot of things for photo decompression and transcoding, not really interesting to us. DLSIM is unusual because we're looking up the address of DLSIM using DLSIM itself, which doesn't make a whole lot of sense until I explain why. So in this challenge, the way I set it up was I saw in real world apps that they would use DLSIM to resolve a function pointer to itself, and then using the function pointer, they would then use DLSIM to resolve other APIs like access and fopen and so on. And again, it's just another abstraction layer to try and conceal what it is they're doing. But ultimately, if we have something like r2frida and we trace a DLSIM, then we're still going to see what's happening. So that's where we can leverage the power of the dynamic analysis. So another API here that stands out is access, and the rest I can tell you ahead of time that these don't really interest us. So access is definitely interesting, and LSTAT is definitely interesting. So if we just read the man pages for access and LSTAT, just in case you haven't already, access is for checking the accessibility or existence of files. And in a similar sense, with LSTAT, we can obtain information about a file path. Now, the interesting thing about both access and LSTAT is that the file path that's being searched for is at the first argument. And if I go back to the access man pages, you can see it's also the first argument. So that makes it a bit easier because we can hook these in a similar way without messing around too much with different argument indexes. So in both cases, we just want argument 1, which would be register x0. So the application crashed in this case because although we were monitoring the calls to DLSIM and we now see the APIs they're looking up, they're still detecting us, and we haven't been able to stop that from happening yet. So what we're going to go ahead and do is restart the process. And now that we know to hook access and LSTAT, we're going to use \DTF to do so. So DTF allows us to pass a format specifier. Alex showed this briefly in his examples. But basically, you can trace a function and you can specify how you'd like it to be traced. So in our case, we would like to trace the onEnter, which means when the API is being called, we'd like to see the arguments rather than the onExit after the function is run. We don't really care about the backtrace, but depending on the argument types, we may want to print them in a certain format. And if you remember looking here, we're looking at strings. So we can actually just go ahead and trace these APIs, access and LSTAT, by saying we want to print the string and we want to do it in the onEnter, and we can just chain commands with semicolons. So I'm going to do LSTAT as well, and with the exact same format specifier. So we see that that's run. I'm going to clear the console and unpause again so that we can grab all the JSON output. And again, the app will detect us because we're not doing any bypassing yet, but again, we're going to hop into VS Code and just clean up this JSON so that we can parse it. But just like we did before in JQ, we're going to parse output.json again into JQ. This time, we actually get the function name inside the JSON as well as the values. So JQ again allows us to be a little clever here. We can say, we can give it a name. Let's call it API name, and we say that's the API name, and it'll print out only the APIs that are called. But we would also like the values as well, so we can say file path is .values. And in this case, we can see file path is an array, so you can even say in the array we want index 0. So here we can see all of the different calls to access and LSTAT. We can see the file path looks like there's some Frida detection. We can see the flag for challenge 1. There's some legitimate things in here as well. the application is looking up the existence of genuine files. But a lot of these things are, related to jailbreaks and jailbreak detection. And it seems like they just call it with both APIs, right? Maybe just to make sure that we've not hooked one, that they catch us with the other. So in this case, we're going to want to go ahead and parse out the file paths. Since in this case, the file paths are duplicates across the two APIs, we're just going to print out value 0. And as before, I'm going to sort and make it unique and pass it into pbcopy. So pbcopy on Mac just puts it into the clipboard, and we're going to go ahead and write a bypass for this. So I'm going to save it as bypass1.js. So we're going to write some Frida code here. So the first thing that we're going to do is we're going to get rid of these /escaped double quotes and just get rid of them completely. So I'm not going to replace them with anything, just replace them with nothing. And then since we're working with JavaScript, we're going to replace the double quotes with single quotes. So the other thing that we can do here is we want to turn this into an array. Now there's probably some kung fu that you can do inside Visual Code. Some smarter people than me probably know it, but if you turn on the regedit search, you can search for apostrophe new line, and we'll just stick a comma in there so that we turn these into array items. So let me make this a little bit bigger, and we can get rid of that, and we can go up here and say as list equals, and then for all of this, we're just going to format the document. Now, some of these we don't really care about. So there's a lot of these things that are jailbreak detections. But for example, all of these system things, we don't care. We can get rid of them. All of the private var container stuff is to do with the app. We can get rid of that. We can get rid of these two as well. We have local time and the application bundle. We can also get rid of that, and the font cache, we don't care. App config, not interesting. URL config, not interesting. The flag itself isn't a file path. It's just something that we had to observe. So we're going to get rid of that, but we'll handle that in a special case in just a second. So now we have a list of all the things that we're going to bypass, and our two targets that we need to influence the behavior of are access and lstat. So we're going to create a little array of these as well. Access, lstat, and on that list, what we're going to do is we're going to run a for each, and we're going to say API for each loop, and then we're just going to resolve the symbol through Frida. So we're going to say module dot find export by name, and these things exist in libsystem. So we're going to go ahead and grab them from there. And then using Frida, we can use interceptor.attach with a symbol, and we can go ahead and write our on enter and on leave. When you're on enter, we can get access to the arguments of the function as it's being called, and in the on leave, we get an opportunity to observe and influence the return value as well. So we obviously want to change the return value for these specific files, but not for anything else, so that we don't break the app. So one of the cool things that you can do is inside the on enter, you can pass things or make things accessible to the on leave by using this. So I can say, for example, this.path is arg0, and we saw that it's a char pointer, so we're going to read UTF-8 string and pass it into the on leave where we can actually check it. In the on leave, what we want to do is another for each, and we can just say, let's loop over all of these file paths, and we can just say if this.path is equal to the entry of the array that we're looking at, then we're just going to print out a little message to say bypassing file path, and we can print this.path. So we need to change the return value, and to do that, we can just do return value.replace, and we'll just replace it with all f's. And in the else, we're just going to handle our special case here. So we just want to print the flag just so that we've got a fully complete solution. And we can just say else if this.path, and we could say starts with, and we can put that in there. So we can say inside our console.log that we've found the flag, and we can print this.path. So that should be complete. We should print out and bypass only the file paths in the list that we've observed in r2frida, and we're targeting both access and lstat. And also, if we do happen to see the flag, then we're going to print that out as well. So fingers crossed this should work. Demo gods permitting. So we're going to go ahead and jump back into r2frida. I will go ahead and open the app. We're going to load it now using \dot, and you can just pass in your JavaScript file, and then we're going to resume. And this looks promising. The app is running. It says that it's self-destructing, but nothing has crashed, as you can see. And in the logs, we can see all the file paths that are being searched for. We see them twice because, as we observed, they call it once with access and they call it once with lstat. So it's expected that we'll see each thing twice. And we don't have to print these on the screen. It's nice to see that everything is working. And of course, there is our flag. So with that, we can now start to look at challenge 2. If I try and click the I'm ready button, it doesn't actually let us get to challenge 2. So we have to find a way to figure out how this button and this passcode field works so that we can actually get past it. So just to be nice and clean, since I've restarted a bunch of times, I'm gonna quit out and start from scratch. So here, I'm gonna import bypass1 again and resume. Ahead and clear the buffer. But just like before, I'm going to run the init, and then I'm going to pull in the imports, symbols, libraries, which again is already done, but just force of habit on my part. So I'm going to pull in all of that information, and I also want some information on this first view controller, which we looked at earlier. So I'm going to do it also without the dot, just so we can print them out. So looking at the screen, we can see that there's an I'm ready button, and there's a function called I'm ready pressed, which is logical to assume, okay, when we press that button, this is the function that's going to run. So let's go ahead and seek there. We're going to turn off not skip again, and we're just going to analyze the function. So inside this function, we can print the instructions. We can also, if you have it installed, you can also use PDG to leverage the Gidra decompiler, or you can use the other decompilers in R2 as well if that's easier for you. But here, just make this a little bit smaller since it's screen. So for some reason, the symbol names are a little bit weird, so we can go ahead and spend a few seconds just cleaning these up. Using AFN to rename. So we're just going to remove all the gibberish from these. That's a nice cheap way. Since we're only doing a basic example, this will be fine. Objective-C, send. We also have calls to string length. So we also have string end compare. And we could just rename all of these. And some of these other ones don't really matter, but all of the ones that we really care about will be present now. So again, I'm going to print the output just so we can see some of these that are cleaned up. So the Objective-C message sends are cleaned up, so are the NS logs. You'll notice that the strings for the method name aren't resolved. We could actually print the pointer value there, so we can get the address of the string, and then we can print the string. So we can see the method name or selector, since they're passed as strings in Objective-C. But there is a nice script that Alex included in the GitHub. So you can import the cfstring.js, and we can go ahead and run that as well. Like so. So now when we print the outputs, we can see get passphrase, we can see the passcode and text. And if we look at this function, what's happening here is there's a string compare with var38 and var30. And there's two lengths that are calculated that are checked here as well. So basically, it's comparing two strings that need to be the same, and they need to be the same length. Of course, those things go hand in hand. And what's happening is they call a get passphrase function for var30, which is the first thing we're comparing. And then the second thing is actually a passcode field where they get the text value and then they read it as a UTF-8 string, which is this passcode field over here on the right-hand side. So what we really want to look at is this get passphrase function, because that's really the one that's interesting for us. So we're going to go ahead and seek to our get passphrase. And we're just going to print the output. We need to analyze the function first. And we can see it just returns an address. So we can go ahead and print that. And we can see that in this case, I'll move it up a bit. We can see in this case, the string returned by the function is pancakes are better than waffles. So that's the passcode. The only trouble with the passcode is it's going to be really difficult to type that in, since it's all in LeetSpeak and it's large and it's problematic. And if you remember, if we seek back to where we were, all that really matters is that the strings are the same length and the strings are identical. And we have control over one of the strings in the passcode field. So if we could overwrite the function to return the word passcode instead of pancakes are better than waffles, then we would actually be able to bypass this, and that would be much quicker. So to do that, we can actually use the DMA commands to allocate memory on the heap. In this case, we want to allocate a new string. So we can say DMAS, and we'll just call it passcode. Now we've got a pointer to that string on the heap, and there we can print it out. Our string passcode is there. And in the r2frida commands, there's a command called DIS, which allows you to replace the return string of a function, which is perfect for us. So what we want to do is we want to print out the address of the get passphrase function. We can pass that to \dis, and then we can pass our pointer to our string. Now, what should happen is when we click I'm ready, we should advance to challenge 2. And of course, challenge 2 is going to crash because it detects us. But if you watch carefully, you'll see it happen. So we'll click I'm ready, and yep, there we go. We've bypassed the check and we advance to challenge 2. So that's how we've solved challenge 1. We've got past the middle layer and made it to challenge 2 as well. But now we need to actually solve challenge 2. So I'm going to quit out. I'm going to clear the buffer and run again. We're going to run bypass 1, and we're going to resume, so we get all the information again. And this time, instead of we know how to skip the check here to get to level 2, but let's just figure out how we're actually going to solve challenge 2 first. So like before, we're going to run the init. I'm going to grab the imports and symbols this time, and we're also going to list the information for the second view controller, which is challenge 2. So here again, we can pull that information in. So there's this view.load function. We're going to seek there and figure out what's the deal. We want to turn off not skip again, and we're going to analyze. So again, large function has a bit of function inlining and complexities, but no manual obfuscation or anything like that, or no automated obfuscation, I should say. We haven't used OLVM or anything complex, so it's just a bit of a large function. So if we, for example, let's say print 300 instructions, we'll go ahead and do that. We can see, similar to before, we have some Objective-C stuff happening. We can see some ANDs and XORs. But what's interesting is that there are these SVC OX80 instructions, which are supervisor calls, as you can see here in the comment in the annotation. So supervisor call is a way that the userland code can ask for kernel code to be invoked. And what normally happens is if, for example, you call the exit function in libsystem then exit will invoke the appropriate system call for exit in the kernel, and then the kernel will actually go ahead and take care of that for you. And in some cases, applications try and be sneaky, and instead of calling the APIs that we're monitoring, like lstat and access, they can do it through these supervisor instructions by setting up all of the correct arguments in the registers and then running this instruction. So that's a sneaky way that they might be catching us. And thankfully, with r2frida, it's super easy to get past these. So if we want, we can use \dm, which will list all the memory ranges. And the reason we're going to do that is because we only want to focus on our crackme, and we only want the executable region where the code resides. So we can seek there. And then using this \e/, we can set the appropriate search parameters if we put a full stop. So we're going to go ahead and do that. And now, for example, if I print out the search from, you'll see that the two addresses match. And this is just defining where we want to search. And we're looking for SVC OX80, and that can be quite slow. But if we can search with the hex pairs, this would be much faster. So the PA command in R2 allows us to specify the instructions, and it'll tell us the opcodes. So we can say OX80, and we get our opcodes back. And in r2frida, you can search with \/x to search for a hex pair. So we can go ahead and pass our opcodes like this. And we get 63 hits in total. So we found 63 places where they're trying to be really sneaky and stop us from finding out what they're doing. And what you can do is we want to basically get rid of all of these. So if I show you, I'm going to print one instruction at each of those locations. So you can, in R2, you can use iterators with the @ signs to do things over multiple locations. So here we can see all the instructions are currently SVC OX80, right? So there's 63 of these supervisor calls. But in the same way, we can actually use the WAO command to write a NOP, a no operation. So we can replace that supervisor call with an operation that does nothing, and that will essentially bypass these checks. We're going to go ahead and write a NOP at all locations. And if I go ahead and print them all out again, you'll see it says NOP now instead of SVC OX80. So we've essentially circumvented all of the checks, but the trouble is we want to see what the checks actually do. So just like we did before, we can use dynamic trace register. And in this case, we're going to use $, which means the current address, the currently seeked offset. And we're going to do that and print out argument register x0. And we're going to do that at all of the hit locations. So for all of the hit locations, we want to trace those points in code, and we want to print out the value of register x0. So for each of these locations will be populated in $, and the trace will be inserted. And this means that when we run challenge 2, we'll get access to all of the things that are being searched for. Okay, so we need to go ahead and quickly bypass this little button again. But if you remember, we just want to stick passcode on the heap. And we can go ahead and do first view controller. And we can do dis get passphrase, and then our pointer to our passcode. And then if we hit I'm ready, we should go to challenge 2. And now you see that it doesn't crash. It no longer detects us on breaks because we've inserted the NOP instructions and overwritten all of their checks. And just like we did previously, I'm going to parse the JSON output with JQ since it's super nice. So we're going to go and clean that up, hit save, and then let's take a look at what's actually happening. So at output JSON into JQ. Here we can see lots of output again, and we just want to narrow in on the values on x0. So let's go ahead and do values x0. And here are all of the file paths that the application was searching for. And you can see right at the very bottom here, we have the flag for challenge 2. So this is, as I say, it was last year's Crack Me, there was a very small R2Frida script, maybe 4 or 5 lines, that was showing the solution. So I figured it would be a good idea to showcase how you would actually think about the problem, how you would walk through it and understand what's happening, the different commands you might use to actually get to the final solution. You can build a small R2Frida script that does all of this automatically without having to manually insert addresses or run commands. You can have it work all of it out for you, which is super nice. And if anyone's interested, we can always show you that afterwards. So that is it. I am done with my section. I didn't get a chance to read the chat yet to see the questions, but if you have questions, we can take a look at them. Otherwise, we'll take another break before we get started on Android with Eduardo, and I'll be hanging around in the break to answer the questions you might have. I see there are some now, so we can go ahead and take a look. So yeah, back to you, Pancake.
Hi. So we are going to start now with the Android side. The agenda for the Android walkthrough is going to be like an intro to the Android Crackme. So we are going to solve the Cybertruck Challenge 2019 that it was developed by NowSecure to help students or people that they were starting in the automotive market. And the idea, the goal of this Crackme, it was how to teach people to start with mobile security on Android. And the idea of designing the CTF, it was like trying to simulate like a kind of like a mobile app that allowed you to open like a car without having the keys. So it's like a keyless system. So we will be solving like 3 challenges. Each of these challenges, it has one static and one dynamic flag. We can solve the dynamic statically, we can solve the static dynamically, but we will be solving in both ways. And there is like a bonus if we have some time to bypass some tamper-proof, some like dummy Frida detection. So say that, I think we can go to share my screen. So, okay, let me give me a second. Okay, I will download this thing. Yeah. So, okay, I will show my pixel here. For the workshop, we are going to use like an Android emulator from Android Studio. So I'm gonna use like a Pixel 2, 64 bits. Without the Google Play, just to have root in there. So, the first thing we are going to do is to open code. We're going to open the Cybertruck Challenge folder. Once it's open, I will show you here. Yeah, there we go. So I think it was better to remove this. So the first thing I would like to show you is the README. You can find it here. I'm going to explain you the structure of the Crackme. So the Crackme has some slides that I used to present this during the workshop, but it was like also 1 hour in the US, in Detroit. There is like an APK, like a compiled APK that's the one we're going to use that allow us to unlock up to 3 vehicles. Do you have the source code in case you want to double check? You have some nodes. You have some solutions. Very important for you is to use this folder that contains like a template, because we are not going to write the whole, Frida code. So we are going to take like a template as example, and after that we will be starting. So one of the requirements is that for the tamper-proof detection, we have to have Frida with this name in this location, just to let you know. The tamper-proof is here, so it's only happening when you enable the switch. And yeah, the application is like you look like as you see like a button here to unlock, some wiping keys, and yeah, there is no more than that. So the 3 challenges that we will see, as I told you before, they are split in 2: static and dynamic. Sorry. Okay, static and dynamic. And well, in the first one, we need to get like a desk key. So we wanted to teach people the crypto, especially in Android, that is used with the Java APIs. So we wanted to see if the students, they were able to get the desk key, that it was hard coded. There is also like a token generated at runtime, and if the people, they can get it. There is another one with AES, challenge 2, and it say the challenge has been obfuscated with ProGuard, therefore you will not be able to recover the AES key. And we also have like a token, also runtime to allow people to use static analysis and dynamic analysis. And finally, we will have like another 2 flags The one is in the native code, and the other one is also dynamic. So this challenge, it will be generated at runtime. So you have some write-ups here, just in case you want to see another solutions that we didn't provide, and you will see that they are different opinions. So say that, I think we can already start with the emulator. So I put the emulator here on my right side. Okay. So the first thing we can do is we can clean the load cut here. As you see, I have been already searching for like a tag, cyber tag challenge. That's the one that is for the crack me. So I started the load cut here to see the logs. Frida server is already running on my Android emulator. You also have the version that I'm using here. I'm using almost the latest, but I'm using this one. So there was another fix yesterday for iOS, but I didn't need it, so I didn't take it. Okay, so I was explaining before. We can see here, we can see spawn, the application. As we don't know maybe the process name or the package name, we can see that this is going to be made by NowSecure. So we can find it here on, I think is, okay, I don't remember how was this. Spawn, USB, only one. Okay. This one. Okay, so, oh, the application is not running. Okay, good. This is not either. This application. Okay. I think I was right. Sorry, I missed like one slash. So this is the package name of the application. So we can do now R2 Frida. So we use the IO plugin. Then we want to specify the action that we want to do. We want to spawn the application, and then USB. We use like 2 slashes to allow to don't enter the device ID, and then we put this. So once we have it here, we can see that the application is killed and started, suspended. I can do DC, dynamic continue. So the application is running. So the first thing we're going to do is to inspect what the application is doing. So we can play a little bit with the app. So we see that there are some wiping keys. We don't see any load cut here. We can press unlock. And we see like 3 logs, 3 lines with the 3 car IDs unlocking the keys for these cars. So we can also see, for example, the tamper detection. If we press tamper proof, just to be able to bypass it, the application says tampering detected, and the application crashes. Okay, once we have seen this, we can reopen the application again. Once the application is respawned, we can continue. The application is on my right side. And one of the things we can do, well, one of the things I missed to explain is that if we compare iOS and Android, on Android you have Java, the Java layer and the native layer. Difference with iOS is that in iOS is basically everything native. So for that, I will be using JDX as the compiler. You can also use JDX from the R2 shell, but for beginners, I think it's better to start with the UI and showing a little bit of the Java code. So yeah, so the application is running, and as Grant and Alex, they were explaining, we can do /IC. So we have like information about the classes. So we can do this like that. Okay, say like this, almost like 10K. We see all the Android framework libraries and everything there. We can search by Cybertruck, or we can search by NowSecure. and then we can see what we can see. Okay, so as you see here, you have my keywords that I was searching for. So you have the main activity. Without doing any static analysis, I'm supposing that that's going to be the first activity that is launched, and we can also see that the challenge ones maybe is this class, the hook detector that we have in here, the switch, the tamper-proof, and probably this or one of these ones is going to be the challenge 2, the one that he was saying that he was obfuscated with Progar. So Progar, if you don't configure anything by default, is giving like letters in lowercase, like A, B, C, D, and it's doing overloading for methods and for classes. So say that we can also see, what we can do with IC. So when I don't know what the command is doing or I don't remember anything, I remember as you can do / the command I want to and question mark, and I can see things. So for example, if I want to see the methods that one class has, for example, if I want to do the hook detector, so I want to see the methods that this class has. So I can see that, yeah, it's not too big. So it has like the constructor of this class, and has like a method that is called is Frida server in device, and is returning Boolean. So I can give you like a hint of the bypass. We will have to hook this function and return supposedly like false. So Frida is not in the device. But yeah, so this is something we can see in the Java side. We will be covering this part with a decompiler to see everything more in detail. We can also move to the dynamic to cover the challenge 3, the 2 flags that are in the challenge 3. And as we can do now, it's like same command, / information libraries, IL, and I can do it without grabbing anything. And let me open this maybe bigger for you. So we can see basically all the process memory and all the libraries from Android and everything. Normally, at the end, they're the libraries that they are implemented for the application. In this case, I don't see what is. Okay, here. So normally on Android, when you create like a native project, if you don't modify anything, the native library, it will be called like lib. But anyway, it's not something you need to know, but I can tell you that this is the name. So once we know that this is the name, we can search by keyword, for example, here. And we can see the object here. And once we have the object, we can seek into the object. So we jump there, we jump into this library. We can see that this is the ELF in memory. So this is the share object in memory. And one of the things we can do is we can see the exports. So remember, / for r2con2020 commands, I for information, and capital E for exports. Okay, we can only see one that is main activity init. So that's going to give you like another hint that the main activity is the first activity that is started. And we will have like a native function that is called init, or in the Java side, it will be like a method, and it will be transformed in code in native. So once we have this, we can do the same thing that we did before. We convert this to R2 flags. So now we can do like a seek into like a symbol function, Java now secure Cybertruck main activity. Don't know if this will work on this case, but I'm going to take the R2 flags into my session, in my dynamic session. So I take these things, the imports, the exports in this case. I can do the same thing for imports. So information imports. So all the commands, they have a little bit of idea to remember. So as we see, there are not many imports. You have exit, finalize, Android, log print, and stack cookies, and the string length. We can do the same thing. If we are lucky, we will get the symbol here. Okay, so so once we have been doing this, we can jump, we can seek into this object, as we have like a flag in R2. We can seek into there, and then we can see, like, for example, PD. As you see here, we have the flag that Radare was marking at the beginning. And this is basically like a function. So at this offset, I want to analyze function. So I want to define like a function. So I see the prologue, I see the push, the base pointer, and the stack pointer, and everything. Okay, so I do a function here. And then I can do PDF, so print disassembly function. I'm going to make this bigger for you, just to allow you to see better. So yeah, we have a function. We can see here that is printing the message that we saw in the logcat, and there's some call here. There is another call here. Probably this is the string length that we saw before in the imports, and maybe the exit, probably. I don't know, I'm doing like, assumptions. And the other thing we can see is that there are some reads, there are some reading here. And yeah, I mean, if you are like me, that I like assembly, but I also like the compilers, we can use print decompiler Hydra, and it's taking the compilation of Hydra without going to Java, and then we can see what Hydra is decompiling. So once we are here, we can go up at the beginning. So we see that the function is not returning anything. Probably this is the GNI environment pointer. This would be the this, and we don't see anything going there. So they are not arguments from Java going to native. So we know that they are not input arguments in this function. So we can see that this function has not been, let's say, converted to like one of the imports or one of the functions that we saw before. But we have something here. I can tell you that this function is Android logcat. So we can do print a string at this location, and as you see here, there is the logcat. So this is going to be the message. So we know that this is Android log print, and one of the things that I want to give you is like a couple of seconds to see the function. Something important is that the compiler is giving you some rubbish. I don't know, is the I think it's after the, yeah. So after that, everything is rubbish. So this is, I think this is the stack cookie, and the rest is not important. So what we have to see here is that, remember that we are in dynamic. So we see that, so there are some dereferences here, and from these locations, and they go to the stack. We see all the variables that I think that this is going to be like a buffer without looking at the code or without doing any static analysis. If we extract all the casting and all the references, we will see that there is one variable from the stack that is starting or is ending in 88, and 88 is here. So we can see what is in there. We can do PS just to see if we are lucky and we get something there. And well, we don't get anything there. We can see print exa, and I don't know, let's print 16. Okay, doesn't look like it's fine. Oh, okay, I think I made a mistake. It was this one. Sorry about that. So let's print this location and see what we have there. Okay, we see a comma. Let's see if we have print, let's say 16 bytes. Okay, we have a buffer there. We don't know still what it is, but we know that, so this is going to be like a variable in the stack. And if we look this structure of the decompiler, we will see that there is like a counter here, like maybe we can call it I, the variable for the loop. And this is started here to 0, is incremented here, and is accessing like every time one more and one more. So we have to look at this variable in the stack with 88 at the end and 56, right? If I'm not mistaken, 56 and 88. So we can see here 56, and this is at this location, and 88 is like a difference of 20 in hexa, that is 32. So we take this pointer, this address, and we do print string. And yeah, so we can see there that we have some string. And we can go later to finalize the correctness. So we can see a little bit that with a little bit of dynamic analysis, we have been able to to inspect a little bit. So we can do the same thing for that as we did before, and it will give like a comma, I think, and then if we print hexa of 20 in X, we get like the buffer. So this will be like a XOR of this buffer with this buffer. If we convert it to string to byte array, so we can do like 20 difference. And yeah, so we have these two buffers. This is a string that probably this is the string that we have to give, and this is going to be the other one. So as we see in this assembly, we have an XOR here, and this is like a very basic challenge to solve. So once we have been doing this, we can open the APK. So in order to open the APK, I'm going to close this and do like a copy of the driver track to TMP. Okay. Okay, I know what's going on. So that's going to be well. Okay. Once I have it in TMP, I'm going to open it in JDX. So now we are going to do like a little bit of dynamic analysis for the Java. So we are going to try to solve the first two flags, the first two challenges. We will start with the main activity, as we saw before in dynamic. And when we look at the compilation, we see the main activity. We see that the native library is loaded at the start. We see also the init. When we do like a double click, we see that it's called here in this method. And then we see that this method is starting with like a challenge one. But we can go to onCreate. On onCreate is checking if the Frida is, if the switch has been enabled, and if the switch has been enabled, we can do the Frida detection. If the Frida server is found in the device, we can call system exit with some delay to let the user see the toast in the screen. So we see, as you can see, this is the switch. We can see the other switch that is wiping keys. This is basically like a dummy method. Basically, we don't see that it's doing anything. It's just looking at if it's pressed. If it's pressed, it's like wiping keys. The same as here. If the Boolean C says it's pressed and Frida is in the device, I print the toast. But yeah, we can go to the on-click. When you click on the button, we have the button here. That's going to be the button that does the unlock. If the button has been pressed, we can start, the first thing, like let the user that we are unlocking cars, and the first thing we see is that the main activity has a method, okay, that is starting. So we see the references there, and we find it here. And yeah, so we see that the challenge 1 is coming from key generators. So we go to the package key generator, open the challenge 1, and here we have the first challenge. The first flag that is needed, it was the key, the static key that it was in the application. So this is the first flag. So we have been achieving like 50 points. So this is the first flag that is needed. And after we have this key, we can try to read the code. The compilation in Java, as you can see, is like looking as like a real code. Feel free to check the code after the walkthrough, and you can compare the compilation with real source code. So here, basically, we have a desk key spec constructor getting some bytes as a key. And after that, we have like a secret key object that we instantiate with generate secret. So we pass this key, and then we have a test operation. Once we have this secret key object, we can instantiate like a cipher object instance, and then we can initialize the cipher object with this secret key object, and then we can do final. Okay, so ways of solving this with Frida or r2frida is like we can hook do final, we can hook generate dynamic key, and we can hook this one. And I think the easiest for us is to hook generate dynamic key, that we will see that something is going like input and something is output. So if we go generate key, it's called here in this other that is method that is called generate key, and we see something that's going to be my input. So that's the thing that's going to be encrypted. So this is also getting bytes, and it's calling this function. And if there are no exceptions here for all the crypto padding and illegal block size and other exceptions, we will be printing locking card ID, and we will be getting the key. So basically, as you see, the key is returned, but it's not used for anything. So it's like a basic CTF. So we can now open the template that I was talking about. So once we have here, we can open student. Okay, I'm not in the right place. Let me open it. Code Cybertruck. Okay. Cool. So I have it here. I don't need the README anymore, so I can close it and close it. So we're going to take the student. I think I'm going to overwrite this template to use it as well, like as me. So the first thing we are going to do is to see if this is working and see what we can get. So just to give you an explanation, this is like a Frida JavaScript that contains hooks and also contains some wrappers for compressing this challenge in 45 minutes. And let me see my timer here. Give me a second. Okay, that's fine. And we have some more Java code here, and also some native to enumerate modules and solving the native challenge. So the first we're going to do is to focus on the first one, that is to get the key, the AS key. So we can solve it statically or dynamically. So the first thing we're going to do is come in here. So now we will be needing, we need this. So everything is here, the load card, right here. And then we can now R2, Frida, okay. So we can spawn the application again from the scratch. I think we need to load the scripts that is going to be in Cybertruck, student, okay, cool. Load it. So we have been loading all the Frida hooks in the process. And now we can resume the application. And yeah, we see that the application is alive. Has been printing something for the native. But now, in order to see if the hooks they are triggered, I can press unlock. And we see some errors here because something is incomplete. But say, hey there, challenge one, hook the dynamic key. Okay. So in order to do that, we can go back to the code here. And I'm going to cheat a little bit. So I'm going to open the solutions just to show you the solutions. And here, what we're going to do is copy paste the challenge one statically. Here, static key. So here, they are the to-dos that we need to do. So basically, the thing we need to do is, so we want to get this return value that is that I explained before. It's this return value. So we want to get this return value, and we want to convert it to X and X string, and we want to print it. This is the main goal of this challenge. So we have also a byte array here. Okay, so once we have this thing, I think we can copy this. We are cheating. Okay, and here we see here. Oh no, this is the static key. So what this basically is getting the input and converting this to string, and then printing this. For the dynamic, so it's just. I will explain you at the time I'm already writing. So there, the original call that we have to call is like here. We want to allow people to know what they need to call. And after that, after the call has been happening, before returning to the real code, we want to print this in an X string. So we can cheat here as well. We can copy, and this is basically the conversion. So the original call, it was to call the generate dynamic key with the byte array. We are using the same variable names that we had in the Jeopardy compilation. And then we have the return value, and the return value is going to be here. It's going to be converted from byte array to X. And the dynamic key is going to be print as dynamic key. Also, in addition to that, we also have the byte array that is going as an input, and it's going to be here in A, in this variable A, and it's going to be like an input. So once we have this, we can save it, and we can go back to the code that we have here in r2frida. So so we can open in again, respond the application. With OO, just in case that you don't know what is OO, reopen the current session. Okay, so we open OO, and it say that it's there. We have to reload the hooks. Okay. Okay, if we see that this is not working somehow, we can kill the application here. And kill the session here, which is if we have a job, just to make sure that we kill it. Okay. Okay, so we need to load the hooks that they were in Cybertruck, student. And I hope that I didn't get any. Okay, so we have it here running, and if we press the button now, we will be able to see at least the first two flags. So this is the static flag that we show in the code. This is the input for the key that is using. This is the input that's going to be ciphered with the with this test key, and this is going to be the output. So we have achieving the first challenge. This is the dynamic, and this is the static. Sorry, this is the static. So once we have the first one, we can go to the second one. In order to go to the second one, we can see again the description. Okay, so for the second one, we need to get the AES key, but it says that now it's obfuscated with ProGuard, and we also have to get the dynamic key. Okay, so we do the same thing. We go to JDX. We go here, and if we go to the main activity and we go this here, that's going to be probably the second challenge, that it comes from here, generators A, so finds usage. Okay, here, and here we have the this. So this is very similar to the first one. The only difference is that it's different crypto algorithm. So in this case, we have AES. Here we see the lock in the debug console that is unlocking the car ID too. As we see here, we are reading something from assets. So we can go here and see the assets, and we see data address must be protected. And so this is going to be something that is used. So we know that probably it will be the key. We don't know yet, but this is challenge2.key. So I think it's quite obvious that we have found the first static key. And let me see my timer. I think I lost the timer for a second. Give me a second. Okay, so yeah, we have the input stream. If everything goes well, this input stream is read line by line, and this is getting converted to bytes. And when it's converted to byte, it's we have a string builder, and this is returning like a byte array. Okay. So as we see here, there's a little bit more difficulty because the names, they have been stripped, and we don't see clearly what's happening. So we see like overload in Android, where we have class A, constructor A, and it's calling to constructor A, and method A, and AAA, and variables sometimes are even A. And the same method has different input arguments like context or byte array, byte array. So, so we want to get the dynamic key now. So this, it will be like generate dynamic key, probably. So it gets two input byte arrays, and it's returning like a byte array as well. So the same thing it does before. We have an AES object, secret key spec object that is being used by Cypher, and once it's created and initiated, is calling to do final, and is returning the byte array that we want to. So for that, we need to hook org now secure Cybertruck key generators, class A, method A, but not this method A with context input and byte array output. We want to get this one. So moving to r2frida, we can open the solutions again. We can copy this one. Okay, you challenge 2. Okay, I think it's here, right? Yeah. Okay, so we have the lines that they have been modified, and as we see here, so we say to Frida, I want to hook this class, the key generators class A. We want to call the method A with the one that has 2 byte arrays like input, and it's returning like a byte array as well here in the red. So we call this object AES because we want to remember that it's like an AES implementation. And then we have a function with 2 byte arrays. The first thing we want to do is to convert to string both byte arrays, this byte array and B1. So the first one is going to be the data, and the second one is going to be the AES key, the static key, as we see here. So this is the acronym for static key, and this is input. Once we have this in here, we can do like the original call to this this class, and specifically this method to the A, and then we get the return value. And before we return it, we convert the reference from byte array to X, and we call it dynamic key, and then we print it in the lotcat. So if we have this already there, we can save it, and we can send it here. We put this back again. We can reopen the process. Good. We can load hooks. Yeah, I don't know. I think it's I'm not lucky today, but yeah. So I do jobs. I kill it. Maybe words. Open it from the scratch. Okay. My memory. Okay. So this Cybertruck student, right? And do DC dynamic continue. Okay, so we are in the same path that before. We want to press the unlock, and hopefully we can see the keys. So we press unlock here. We see that the keys, they were generated, and then we see also that we are reading the assets, the ch2.key, a file that contain the static key. And we can also see that we are recovering the dynamic key, the token that it was used to generate the key, and it's going to be this byte array that we are returning here. So we have been getting the 2 keys for unlocking the card number 2. And finally, I don't know how much time I have. So Alex and Grant, please let me know over the Telegram, if you don't mind. I will go for the dynamic challenge. So, okay, I have plenty of time, so no worries. So I think we can reduce this this session. We can. No, I think it's gonna be better if we do it statically now, because before we did it with Hydra at runtime. So we were using the decompilation at runtime to analyze the native library. So I'm going to extract this. Okay. Oh, I think it's already extracted. So yeah. So I have extracted the APK inside of this location. So I'm going to open Radare. Please analyze the APK, the binary. I'm going to say APK. I unpack it here, so it's going to be unpacked already. I'm going to go to the libs. And now I need to choose any of these architectures. Mine is going to be x86-64. I'm in an Android emulator. I use it here. I'm in 64 bits. And after that, I have the native library that we can analyze. And yeah, the application, the binary is already analyzed with capital A. So we can see now analysis function list, and then we can see the list of functions. If you remember in the crack me, if we go to the main activity when the button is pressed, and we go to this K method that is here, there is init. And init is jumping to the native side in this library, and it's doing the unlocking of the keys there. So once we are here, we can seek into the init that we have here. And then we can do PDF. Maybe we want to make this bigger. We can see that this is the function. We can use print decompilation Hydra, and we get the compilation in high-level language. So as you remember before, it's looking like the same. So two arguments, GNI environment pointer and the OTA object this. This is going to be returning nothing, a void. And here we see that the import is there. So we see the load cut. So this is going to be the message. I don't know why this is not taken, but we can see that this is going to be the keylog, the keyless crypto unlocking car ID3. And as before, I already explained. So I think we can explain it here as well. But so we have like a loop with the same structure that before. So we see that the differences between dynamic and static, you know, we can miss some symbols, but the code is very similar. And after that is rubbish, remember, after the stack cookies. But the most important thing here is the same thing. So we see like something called string, like a buffer that is starting here. And yeah, the Hydra decompilation is, it knows that this is string, so it's telling you that this is going to be the string that is going to be in this location. And the XOR is going to happen with another location that is going to be bar 50. And bar 50, where are you? It's going to happen here at 70. And before the other one, it was at 850. There was like a difference of 20 in Excel. So we can do the same thing that we did before. So we can do BS. I think it was at 850, and we should have here the first one. And here we see something that is not, it cannot be represented as like ASCII. So we're going to print EXA as, I don't know, like 0x20. And then we have these two, these 32 bytes where we need to XOR. So the main thing of this this CrackMe is to see that the decompilation in native is not the same as in Java, that everything looks like super readable and super clear. So yeah, so the thing I wanted to do is, as we know, this function is basically returning nothing. So I wanted to allow the students to know about that we can, with R2Frida, we can basically hook at any time at the runtime, any address, and we can get the values. So what about if we get this, you know, we can get this result, and basically we see that this is going to be finally casted to like a byte, and we will see also there. So that's going to take 2 buffers and go one by one of the elements of the array, and it's going to do like an XOR. So we want to basically get this variable, and we want to dereference it and get it. I think with Hydra you can do print disassembly Hydra offset, if I'm not mistaken, and it can give you like a view with offsets and decompiled code. See, maybe I make it maybe smaller for you. So that's going to be around this location. But I think it's better once we have the idea, if we go to the print disassembly instead of the compilation, and then we can print the function. Let's see the place. So I want to see, maybe we can see like a graph here, and we can make it smaller. So we go here, and then we want to identify the loop. So the loop is going to be here. It's going to be here, here, and we have the increment here. And at this location, we will have like an XOR. with two values, ECX and EDX. So these are two Intel registers that we want to take. Okay, once we have this, we can do PDF, and we want to get this offset as the offset of the XOR. So we want to inspect memory at this offset at runtime. So the thing we're going to do now is we are going to come back to r2frida, and we're going to do dynamic analysis, and we are going to get these two registers. We're going to get the values that they are in there. Okay, cool. So let me close this. I don't need R2 anymore. We can come back to r2frida. I think it's in here. So we run the application. Let me load the. Okay, now it works. We resume the application, and if we don't add anything there, it will not happen anything. But so we can go to the place where we have to do. So we say here we are gonna iterate over all the exports of this library, libtarget. Libtarget is gonna be like libnative C, so it's going to be here. So we're going to call this guy with this library name, and so it's going to iterate over all exports, and it's going to see if the export is the init, and once in the init, we want to give the symbol that we got. I think it was 7PD. Don't know if it was this one. Yeah, let me close it and do it again. I don't remember. Oh yeah, I was lucky. Let me take this line and copy this line. Okay, so I'm going to copy this here. So we can overwrite this offset with the one that we want to. And before we do anything, so you see here that you need to do something, you need to complete something. I want to show you that when we are in here and at this offset, we can print all the CPU registers, and we can see that we can see everything at the lowest level. So we can save, and then we can open again r2frida. Let me put my emulator here. I will show you the lotcast there. I open. Okay. Oh, it's not here. PC, where are you? So, okay, / dynamic continue. Okay, good. And now is when the magic happens. If I press unlock, hey, we have seen here probably all the iterations, probably like 0x 20 times, like 32 times that the XOR has been happening. And we see also the previous flags that we were being hooking. And if we see here, let me put the emulator away. So we were interested in two registers that I think it was EDX and ECX. If you see the different lines here, you see like two values. And probably this is basically the thing that we want to get. So as we did before in the static analysis, we know that there are two buffers, that they are being XORed. So with this, we can now do some more elegant printing and don't print all this all these context for all these registers and everything there. We can maybe close this. So everything, so the code again. We can go to the solutions and let me show you here. This is, yeah, and I think this is for 32. So for us, it would be different. We can take these 3 lines and campus student here and do stuff. Now we can paste our lines. Okay, so this it was ECX. So ECX. Okay, and here we have ADX. That is RDX. Okay, so what we are going to do is we are going to get this byte into 2 variables. I call X and Y, and then I will do like an XOR, as we saw in the compiled code. And once I get the calculation here, I'm gonna print this here. I think I'm gonna remove all this. Maybe we don't need it. And I will want to print this, and yeah, hopefully this works. So again, I come back here. I open the application again. Bring the emulator here. Application running again, and my hooks. Please dynamic continue. Okay, I'm there. Press a lock. And okay, we did something wrong, or oh yeah, I know what I did. So we didn't delete the first message that we add at the beginning to see all the context. But no worries, we can do reopen, load again. I don't know why my reopening doesn't work. I think I opened an issue like 1 week in the r2frida repository that it was not working, but yeah. Okay, let me kill it again. We can open it again. Load our hooks before we resume the application. We resume the application. It works, that's fine. And now, if we press unlock, we can see that we have been getting the values that they were in these 2 registers, the 2 arrays. And we are also doing the XOR, and we are printing here. So basically, you can see that the backdoors must always be forbidden. So that's going to be the more complicated flag that we have in the native layer that we have to solve dynamically. You can also do it statically in the code, like a Python script to do it. But as you saw with Frida, it's like a piece of cake. So with this, I think I almost done. I can try to do this tamper-proof switch that we say at the beginning, like a bonus. So once you press this, it's tampering detector. So tamper-proof hooking detector has been triggered, blah, blah, blah. Okay, so as we did before, so we can open in the app. We don't need to load our hooks now. We want to see the classes, and we know that this is happening in one of the Java classes, and we are lucky. We have the symbol there, and we can go here, and then we do \information class method, and we want to see the method, and yeah, this is constructor, and this is the method that we want to. So we can come here, copy this, Okay, where are you? Okay, cool. And here, if we go to detections, to detector, and then we see here that what is happening. Basically, this is returning Boolean, and it's checking that if we have this file in this location in the local TMP folder, or we have this path, or this one, or this one, or this one. So it's basically like very easy to bypass check, and yeah. So we are going to do the same thing. So this is going to be easier, maybe because it's Java. We will do getting this package, this class, and this method. Okay. And the only thing we need to do is return false. So we do the same. We come here. So let me see, hook detector. Okay, it's not maybe in the template. Oh, it's not in the template. Okay, that's good. Anyway, we can add it here. We can go to the solutions. I think I'm overdone. And then, yeah, we can basically take this hook that is in the Java perform, and we can add it here inside of Java perform block callback. And yeah, so just to summarize, hook detector, this method is frida server in device. I get implementation, and in the callback, I print a tamper-proof was bypassed. I don't call the original call, so that's why the way we are going to bypass it, because I don't need to get the return value. I can directly return false. So I save it. I'm here. I'm not going to reopen because I don't know, demo codes. But it doesn't want to work. I'm going to open it from the scratch. So I put my emulator here. I do some cleaning here. And as you see here on my Android, on my path, you have the data local TMP, and then you have the binary Frida server. So I can do Frida, and you can see that yeah, I have almost the latest version of Frida for my emulator, and I have like the binary. In that case, I think it's like a symbolic link to the binary, but it will detect like a file. Okay, so I open r2frida. The application is there. Now want to hook my hooks. I want to add my hooks. /dot is loading the hooks. So yeah, this is some information about the native, getting the all the exports, iterating through all the exports, and getting the offsets and the gate and the address of the export. But now we want to we can press unlock just to get the keys, but we are interested in bypassing the tamper-proof. And yeah, so the application is not crashing, and yeah, we have been bypassing like a super dummy Frida detection, but it can give you like idea of how easy it can be, like sometimes bypass any protection that we have in a mobile app. I think with this we can go to the end of the presentation. So where is the slides are here. Okay. This and so yeah, Alex, Grant, and me, and we would like to give some credits. So this is a list of people that they have been creating r2frida. So the main in the first bullet, we can name Pancake for creating R2, and of course all his contributors, that most of them they're here. And we want to also give kudos to Ula for Frida, and also of course to all his contributors. And we also give thanks to Francesco for all the glue in between R2 and Frida, and especially for R2frida. And of course, we also want to give thank you to all the contributors. And also we want to give thanks to NowSecure for open sourcing and supporting these tools. Thank you. You are awesome. Pancake, I think it's your time. So all for you. Some reference here that I will not spend too much time, so you can take a look if you want extra information about R2Frida. You also get some videos that they were happening in other r2cons, and some webinar from NowSecure. If you have any questions, feel free to let us know over the Telegram group or over the YouTube channel. We will be, hopefully someday, we'll be offering like a 2 days an advanced workshop, 1 day for Android and one day for iOS. So stay tuned. And with this, Pancake, you can take the microphone.
And this is the end of the first day of the r2con conference. I just hope you liked and enjoyed the conference, and we will see you tomorrow. Now it's time to have some dinner and have some drinks. So hope you enjoyed the first day. Bye bye.
Yum, yum.